In the forests of Scandinavia, between 800 and 1100 CE, Norse settlers transformed raw wilderness into architectural marvels using nothing but axes, adzes, and intimate knowledge passed through generations. A Viking longhouse measured anywhere from 15 to 75 meters long and 5 to 8 meters wide, its dimensions determined not by standardized measurements but by the needs of the family, the retainers, the livestock, and the stored goods required to survive months of darkness when snow buried the world shoulder deep. The construction began not with building but with reading the land. A skilled craftsman walked the forest for days, studying how trees grew, which direction they leaned, how wind shaped their crowns. They sought straight-grained oak or pine wood that would split cleanly along its fibers rather than tear across them. The best timber grew on north-facing slopes where trees stretched toward limited sunlight, creating dense, even grain without the twists and knots that plagued sun-drunk southern timber. Each tree was evaluated not just for its trunk but for its roots, which would become knees and brackets, and its branches, which would form rafters. Felling happened in late autumn or winter, when sap retreated deep into roots, leaving wood lighter and more stable. A team of 2 men with double-handled axes could drop a mature oak in half a day, not by chopping through but by creating a precise notch on one side, then a countercut from the opposite direction that allowed the tree's own weight to tear its remaining fibers. The trunk had to fall cleanly, missing neighbors that might splinter it, landing where spring melt wouldn't rot it before processing. Once down, teams used wedges and hammers to split logs along natural grain lines into planks roughly 10 centimeters thick, working with the wood's internal structure rather than against it. The foundation began with selecting stones, not just any. Rocks, Vikings sought granite boulders large enough to remain stable through freeze-thaw cycles, but small enough to position without cranes or pulleys. These stones, each weighing between 50 and 200 kilograms, were arranged in 2 parallel rows marking the longhouse's walls. The stones weren't buried but placed on the surface, distributing the building's weight across their broad faces. Between the rows, the ground was excavated 30 centimeters down, removing organic material that would decompose and settle. This shallow trench was filled with compacted gravel and crushed stone, creating drainage that prevented moisture from wicking into wall timbers. The structural skeleton rose from massive vertical posts, the stockra, each one a single tree trunk, 30 to 40 centimeters in diameter, positioned every 2 to 3 meters along both walls. These posts didn't sit directly on foundation stones, which would wick moisture upward and rot the wood within years. Instead, builders placed flat rocks atop foundation stones, creating small pedestals that lifted post bases above ground moisture. Some builders charred post ends before setting them, the carbon layer acting as waterproofing that could last decades. The posts were positioned slightly inward-leaning, perhaps 2 degrees from vertical, so that when horizontal beams were added, their weight would press posts outward against the soil, creating compression stability. Connecting these posts required joints that modern engineers study for their efficiency. The mortise and tenon, a projection on one beam fitting into a socket on another, was cut entirely with axes and chisels. A skilled craftsman could cut a mortise in under an hour. The socket's walls angled precisely so the tenon would slide in during construction, but couldn't pull out once the building settled. No nails held these joints. Vikings had iron, but it was precious, reserved for door hinges and latch mechanisms. Instead, wooden pegs, called tree nails, made from oak aged 3 years to reach maximum hardness, were driven through holes drilled with bow-powered augers, expanding slightly in their sockets to lock joints permanently. The roof structure began with a ridgepole, the rigaz, stretching the building's entire length at a height of 5 to 6 meters. Supporting this crucial beam required either internal columns that divided the interior into nave and aisles, like a church, or pairs of A-frame trusses every 3 meters. The truss method, which emerged around 900 CE, created clear interior space without obstructing posts. Each truss consisted of two rafters meeting at the peak, held apart at their bases by a horizontal tie beam that prevented the rafters from splaying outward under the roof's weight. This triangular structure, perhaps architecture's most fundamental geometric solution, transferred roof loads directly downward into wall posts, rather than pushing walls outward. Roof covering evolved by region and resources. In Norway's forested interior, builders split thousands of thin shingles from straight-grained pine, each one 30 centimeters long and tapered from 10 millimeters thick at its base to 2 millimeters at its tip. These overlapped like scales, starting at the roof's bottom edge, each row covering half the row below it. Water couldn't penetrate because it followed the grain direction downward, and where shingles met, the overlap created a barrier. In treeless Iceland and Greenland, settlers cut turf-living grass with its root-bound soil layer intact into rectangular blocks 40 centimeters long, 20 wide, and 10 thick. These blocks were laid grass side up in overlapping courses, the grass continuing to grow, its roots binding blocks together into a living roof that could last 50 years. Wall construction revealed sophisticated understanding of thermal dynamics. The simplest technique, stav construction, placed vertical planks edge to edge in, grooves cut into a bottom sill, and the horizontal wall plate below the roof. But planks expand and contract with humidity changes. Oak boards 10 centimeters wide could shrink 5 millimeters in winter's dry cold, creating gaps that admitted wind. More advanced builders used the lath technique, stacking horizontal logs whose ends were notched to interlock at corners. Each log was adzed flat on top and rounded on its bottom, creating a curved contact surface that shed water while the flat top provided a stable surface for the next log. As logs dried and shrank, their weight compressed the wall, tightening joints rather than opening gaps. Between wall timbers, builders packed moss, particularly sphagnum, which grows in every Scandinavian bog. This moss doesn't just fill gaps, it possesses antiseptic properties that prevent rot while remaining flexible enough to accommodate wood movement. In autumn, women and children gathered moss by the cartload, drying it thoroughly before stuffing it into every crack and crevice. Come spring, they would inspect walls, adding fresh moss where wind had worked it loose. Some builders mixed the moss with animal hair, sheep's wool, or horse mane, creating a primitive felt that had better insulation properties than moss alone. The interior floor tells stories modern archaeology slowly deciphers. The central hearth, a rectangle of stones 2 meters long and 1 wide, sat directly on earth or on a clay platform, positioned precisely in the Longhouses' center where roof height peaked, allowing smoke to rise and disperse before seeking exit holes in gables. On either side of the hearth, builders constructed benches thilly that served as seats during the day and beds at night. These weren't simple platforms but sophisticated constructions. Vertical posts every meter supported horizontal planks that created the bench surface, while the space beneath stored food, tools, and treasures. The benches stood 50 centimeters high, lifting sleepers above floor-level cold air, and measured 2 meters deep, enough for multiple people to sleep side by side, sharing body warmth under furs and woven blankets. The high seat Unvegi occupied the place of honor on the north-facing bench, as far as possible from the door's drafts. This seat, reserved for the household's patriarch, often featured carved posts at its corners, representations of gods, ancestors, or protective spirits. When a family moved to new lands, as happened during Iceland's settlement after 870 CE, they took these posts with them, throwing them overboard as they approached land and building their new longhouse wherever the posts washed ashore. This practice wasn't superstition but practical jurisprudence. It provided a random, therefore uncontestable, method of land selection that prevented disputes. Light entered through small windows, vindauga, literally wind eyes measuring roughly 20 by 30 centimeters, positioned high on walls to prevent heat loss. These openings weren't glazed with glass, which Vikings knew existed but couldn't manufacture affordably. Instead, They stretched sheep intestines that had been cleaned, scraped translucent, and dried into a membrane that admitted dim light while blocking wind. In winter, these were covered from inside with wooden shutters, sealing the house into darkness. The primary light source became the hearth fire and oil lamps, shallow soapstone dishes, burning seal oil or whale blubber, their dim, smoky flames supplementing firelight during endless winter darkness. Smoke management reveals engineering sophistication that modern buildings sometimes forget. The longhouse had no chimney. Smoke rose naturally, collecting under the roof's peak where it found exit through louvers, adjustable openings in the gable ends controlled by sliding wooden panels. This smoke layer, maintained between roof peak and human head height, served multiple purposes. It cured meat, hanging from rafters, preserved roof timbers by coating them with creosote, and killed insects and parasites. The smoke's movement created gentle air circulation, drawing fresh air through floor-level cracks and pushing stale air upward, a passive ventilation system requiring no mechanical intervention. Temperature regulation in a building that housed both humans and livestock required understanding that animals generate significant heat. A single cow produces roughly 1 kilowatt of heat, equivalent to a small electric heater through metabolic processes. 10 cows in the longhouse's livestock section, separated from human quarters by a wattle partition, could maintain interior temperatures 10 to 15 degrees Celsius above exterior during winter's coldest months. This heat rose through the partition and spread through the building's shared airspace. The animals benefited from human activities, cooking fires, body heat from a dozen sleeping people, creating a symbiotic thermal relationship that kept both species alive when exterior temperatures dropped to -30 degrees Celsius. The door, always on the building's long side rather than its end, faced south when possible, capturing winter's low-angle sunlight. It measured perhaps 120 centimeters high and 70 wide, deliberately small to minimize heat loss, requiring even tall men to duck when entering. The door frame was a structural element, its posts extending from foundation to roof plate, providing additional support for the building's skeleton. The door itself consisted of vertical planks held together by horizontal battens and attached to the frame by iron hinges forged in the longhouse's own smithy or traded from specialized craftsmen. A simple wooden latch secured it from inside, while an external lock, if the family possessed one, used an iron key 20 centimeters long, worn on a belt or chain as both tool and status symbol. Beyond the main hall, some longhouses included specialized rooms, bower chambers for women's weaving work, storage closets for valuables, even small privies built into the wall's thickness. These spaces were partitioned with wattle and daub, woven hazel withies, covered with clay, mixed with straw and animal dung, creating walls that provided privacy and some thermal mass but weren't structural. The weaving room required good light, so it occupied the building's south-facing end where windows could be larger without causing excessive heat loss. Vertical looms stood against walls, their warp threads tensioned by clay or stone weights, producing wool fabric that would become clothing, bedding, and sailcloth. The longhouse's lifespan varied dramatically by maintenance and climate. In Iceland's harsh coastal environment, where salt spray corroded iron and winter storms tore at roofs, a building might last 30 years before requiring substantial reconstruction. In Norway's sheltered valleys, with regular maintenance replacing rotten sill beams, renewing turf roofs, repacking moss insulation, the same structure could serve 3 generations, perhaps 75 years. Eventually, though, all wooden buildings faced the same fate. When a longhouse became uninhabitable, settlers often built new structures directly atop the old foundation, the original building's remains forming a slight mound, a tell, like those in the Middle East that preserved lower levels for archaeologists centuries later. Modern excavations revealed details written texts never recorded. At Borg in Norway's Lofoten Islands, archaeologists found post holes from a chieftain's hall measuring 83 meters long, among the largest known, with evidence of gold working, exotic imported goods, and centralized cooking facilities that suggest feasting for dozens of retainers. At Longhouses Meadows in Newfoundland, the only confirmed Viking settlement in North America, 3 halls yielded iron nails, a bronze pin, and jasper, fire strikers mundane objects that prove Norse presence 500 years before Columbus. These excavations combine with experimental archaeology, modern builders constructing replica longhouses using period tools and techniques to recover knowledge that died with the last traditional builders. What archaeology cannot fully capture is the social world these buildings contained. The longhouse wasn't merely shelter, but the fundamental unit of Norse society, the physical manifestation of kinship obligations and hierarchical relationships. Everyone knew their place. Literally, where you sat determined your status. From the high seat's honor to the spot nearest the door, coldest and closest to livestock, occupied by thralls. The building's warmth and protection came with social costs, constant proximity, zero privacy, and enforced cooperation during months when venturing outside risked death. These conditions shaped Norse culture, emphasizing loyalty, hospitality, and reputation, because survival required functioning as a collective unit bound by timber walls. The longhouse tradition ended not through sudden abandonment, but gradual evolution, as Scandinavia Christianized and urbanized after 1000 CE. Churches introduced new architectural principles: stone construction, vertical emphasis, separation of spaces by function rather than rank. Growing towns offered specialized buildings, separate houses for sleeping, working, and gathering, replacing the longhouse's multifunctional space. By 1300 CE, rural farmers still built long buildings, but these were primarily barns for livestock, with families occupying smaller, separate dwellings that offered privacy and easier heating. Yet, the longhouse's influence persists in unexpected ways. The Viking expansion between 800 and 1000 CE spread Norse building techniques to Iceland, Greenland, and briefly to North America. In Iceland, turf construction continued until the 20th century. Photographs from the 1900s showing farms whose buildings differ little from those their ancestors built 1,000 years earlier. The Icelandic word for family fjölskylda literally means many under the same cover, preserving in language what has disappeared from landscape. The understanding that buildings shape the people who inhabit them as much as people shape their buildings. Standing in the reconstructed longhouse at Trelleborg in Denmark, built according to archaeological evidence from the original Viking ring fortress, visitors experience something written descriptions cannot convey: the dimness despite midday sun, the pervasive smell of smoke and earth, the way sounds echo in the long hall, the sense of compression from the low roof and narrow windows. These sensations remind us that the past was not merely different in its thoughts and customs, but in its fundamental sensory environment. The Vikings who built these structures possessed skills. Modern builders have forgotten the ability to judge wood by its smell and heft, to estimate angles without measurement tools, to create joints that would hold for generations using nothing but axes and patience. The longhouse represents humanity's oldest architectural challenge, creating shelter that protects while using only materials the landscape provides. Vikings solved this problem with remarkable efficiency, building structures that required no transportation infrastructure, no currency economy, and no centralized manufacturing, yet provided everything a family needed to survive. This self-sufficiency came at a cost. Each building demanded thousands of hours of skilled labor, and construction knowledge passed through apprenticeship, father to son, master to student, creating dependency on generational transmission that made the tradition vulnerable to disruption. What we've discovered through excavation and experiment is only the beginning of understanding. How did builders waterproof turf roofs in Iceland's near-constant rain? What techniques prevented rot in sill beams sitting directly on damp ground? How did they calculate proper roof angles without mathematics, ensuring snow would slide off but wind wouldn't tear shingles away? These questions remain partially answered, the evidence fragmentary, the tradition interrupted, but deeper questions linger. Why did the longhouse form persist so consistently across Scandinavia when local conditions varied dramatically? What social or psychological needs did this architecture fulfill beyond mere shelter? Did the enforced proximity and hierarchy embedded in longhouse living shape Norse expansion, their willingness to cross oceans, their emphasis on reputation over privacy, their complex gift economies that bound people through obligations? The longhouse stands at the intersection of material culture and social structure, reminding us that architecture is never just buildings, but the physical manifestation of how people understand relationships, hierarchy, and belonging. In those timber halls, surrounded by family, retainers, livestock, and the smell of smoke and earth, Vikings didn't just survive Scandinavian winters, they created the social bonds that would carry their culture from Baghdad to Newfoundland, from farming valleys to trading ports, building not just wooden walls but the foundation of medieval northern Europe. In the year 793, a ship materialized from morning fog off the coast of Lindisfarne, carrying warriors who would redefine maritime warfare. That vessel represented not sudden innovation but the culmination of centuries of shipbuilding evolution, each generation solving problems their predecessors couldn't, building knowledge in timber and tar until Norse craftsmen created ships that could cross the North Atlantic, navigate rivers barely a meter deep, and beach on shores without harbors. The technology that made Viking expansion possible existed not in written manuals, but in the hands of master shipwrights who learned their trade through decades of apprenticeship, measuring nothing, calculating nothing, yet producing vessels of such precision that modern naval architects study their designs with respect bordering on awe. The transformation began in Scandinavia's Bronze Age, perhaps 1500 BCE, when builders hollowed single logs into primitive boats. By 500 BCE, they had discovered that adding planks to a dugout's sides increased carrying capacity without proportionally increasing weight. This plank-on-frame technique evolved slowly, constrained by available tools, stone axes that could fell trees but couldn't shape planks with precision. The advent of iron tools around 200 BCE accelerated everything. Iron axes allowed controlled splitting along grain lines. Iron adzes could hollow curves and fair surfaces. Iron augers drilled precise holes for rivets and trenails. Each tool advancement enabled construction techniques previously impossible, and by the time of the Roman Empire's fall in 476 CE, Scandinavian builders had developed clinker construction, overlapping planks fastened with iron rivets that would define Norse shipbuilding for the next 6 centuries. The Gokstad ship, excavated in 1880 from a Norwegian burial mound and now displayed in Oslo, reveals this technology at its peak. Built around 890 CE, she measures 23.3 meters long, 5.2 meters wide at her beam, and draws just under 1 meter of water when loaded. Her hull consists of 16 strakes, horizontal planks running the ship's length, each carved from a single oak tree and shaped to follow curves so subtle that measuring them requires laser scanning. The lowest 9 strakes, comprising the underwater hull, overlap each other by 2.5 centimeters, creating a flexible structure that bends with wave action rather than resisting it. Iron rivets, spaced every 15 centimeters, clamp the strakes together, but between them, gaps remain, not construction flaws, but deliberate features that allow individual planks to flex independently. This flexibility transforms the ship into something alive. Modern replica vessels, built using archaeological evidence and period tools, demonstrate that in heavy seas the hull twists visibly, the prow and stern moving out of alignment by several centimeters as waves pass beneath. The clinker construction's overlapping planks slide minutely against each other, absorbing energy that would crack a rigid hull. Naval architects call this characteristic working, and while it sounds like structural failure, it's actually sophisticated engineering. The hull works with the sea, not against it, distributing stress across the entire structure rather than concentrating it at joints. This requires wood selection of extraordinary precision oak cut from the same forest, felled in the same season, so grain structure and moisture content remain consistent throughout the vessel. Shaping these planks demanded tools and techniques modern builders struggle to replicate. The process began by splitting logs radially from the center, following natural grain lines that spiral through the tree as it grew. A shipwright would study the split faces, reading the grain-like text, selecting sections where fibers ran nearly parallel for 20 meters without significant deviation. These sections were further split into rough planks, using wooden wedges and beetles, heavy mallets that drove wedges deeper with each blow. The resulting planks, still rough and irregular, were shaped with broadaxes and adzes, tools requiring decades to master. An experienced craftsman could remove 1 millimeter thick shavings with each stroke, gradually revealing the plank's final form. The keel kjola in Old Norse formed the ship's backbone, a single oak beam sometimes exceeding 20 meters in length, finding trees of sufficient size, straightness, and grain quality required searching entire forests. The ideal tree grew on a slope, its trunk curving slightly to follow the hillside, creating natural rocker, the keel's gentle upward curve at bow and stern that helped the ship turn. Once felled and shaped, the keel was laid on level ground, and construction proceeded outward and upward from this central element. The first strakes, called garboard strakes, attached to the keel's sides through precisely cut rabbets, L-shaped grooves that cradled the plank's lower edge, while allowing its upper edge to overlap the next strake. Stem and stern posts, the ship's bow and stern terminals, required extraordinary craftsmanship. These weren't separate pieces attached to the keel, but integral extensions, the transition from horizontal keel to vertical post carved from a single piece of wood that might weigh 300 kilograms. The wood grain had to follow the curve continuously, without breaks or cross-grain sections that would create weak points. Builders sought trees that grew with natural curves, oaks that had been bent as saplings by landslides or wind, and had healed to create the exact curve needed. Finding such trees was so difficult that stem and stern posts were sometimes salvaged from old ships and reused, their proven strength worth more than newly shaped wood. As strakes climbed higher, the hull's shape emerged not from drawings or templates but from the builder's internalized understanding of hydrodynamics. The entry angle, where the bow meets water, had to be fine enough to slice through waves without resistance, but full enough to provide buoyancy and prevent the prow from diving. The run how the hull narrows toward the stern needed to allow water to close smoothly behind the ship without creating drag-inducing turbulence. These considerations required balancing opposing demands. A narrow hull moves faster but carries less cargo and is less stable. A wide hull is stable and capacious, but slower. Viking shipwrights solved this by varying hull shapes for different purposes. Warships, built for speed and coastal raiding, were long and narrow. The Roskilde 6 ship measured 37 meters long but only 4 meters wide, a length-to-beam ratio of 9:1. Trading vessels, built for cargo capacity and ocean crossings, were shorter and beamier. Typical Nars measured 16 meters long and 5 meters wide, a ratio of just over 3:1. The strakes above the waterline underwent a critical transition. Underwater, planks were smooth and tightly fitted to reduce drag. Above water, builders wanted strength without excessive weight, so strakes became progressively thinner, decreasing from 3 centimeters thick below the waterline to 2 centimeters or less for the uppermost strakes. This weight reduction high in the hull lowered the center of gravity, improving stability. The topmost strake, called the sheer strake, required special attention because it defined the ship's profile and bore the stress of oar ports, circular or rectangular holes cut through the plank where oars extended over the side. OR port construction reveals problem-solving ingenuity. Simply cutting holes through the strake would weaken it catastrophically. Instead, builders cut the hole, then reinforced its edges with separate pieces of wood, creating a collar that distributed stress around the opening. On the Gokstad ship, these ports appear to have been closable. They're positioned so wooden discs could seal them from inside when under sail, preventing waves from entering. 16 pairs of oar ports line each side, indicating a crew of 32 rowers when under oar power. Yet the ship also carried a single square sail of roughly 90 square meters, meaning she could be propelled by wind or muscle depending on conditions, providing redundancy critical for ocean crossings, where failure meant death. The internal framing system, the ribs, that give a ship its structure, employed a technique that baffles modern builders familiar with frame-first construction. Norse ships were built shell-first. The planking was erected first, creating a flexible shell. Then frames were added inside to stiffen and support it. These frames weren't attached to every strake, but only to alternating ones, using lashing rather than rigid fasteners. Spruce roots, stripped of bark and split lengthwise, threaded through holes drilled in both frame and strake, creating flexible joints that allowed the hull to work while maintaining structural integrity. This lashing system meant the hull could be partially disassembled for repair. A damaged strake could be replaced by cutting the lashings, removing the plank, shaping a replacement, and relashing it into position. The mast and rigging represented the ship's most complex engineering challenge. The mast mastery in Old Norse stood approximately 12 meters tall on a ship like the Gokstad vessel, supporting a sail weighing perhaps 100 kilograms. This generated enormous loads, not just the mast's weight but the wind pressure on the sail, which in a strong wind could exceed several tons. Distributing these loads required a mast support system more sophisticated than simply stepping the mast into a hole. The mast fish curling was a massive oak beam, nearly 4 meters long, positioned athwart ships across multiple ribs at the ship's widest point. This beam featured a large slot into which the mast's foot fitted, held in place by a wedge. The mast partner mast beam was a second substantial beam at deck level, preventing the mast from moving laterally while allowing it to be raised or lowered. Why design a mast that could be lowered? Rivers and bridges. Viking ships operated not just at sea, but deep into river systems where bridges blocked passage. The ability to lower the mast transformed the ship from purely maritime vessel to amphibious transport capable of penetrating hundreds of kilometers inland. The Gokstad ship's mast could be lowered and raised by a crew, using the forestay, and the rope running from mast top to prow as a pulley system, allowing the 30-ton vessel to pass under bridges, then re-raise the mast and continue upriver. This capability explains how Norse raiders appeared without warning deep in Francia, their ships having navigated the Seine, Loire, and Rhine far beyond where coastal vessels could reach. The sail itself represented a massive investment of resources and labour. A square sail of 90 square meters required wool from approximately 200 sheep, the threads spun by hand, hundreds of hours of work, then woven on a vertical loom over several months. The finished cloth was thick and dense, perhaps 500 grams per square meter, making the complete sail weigh over 45 kilograms even when dry. In rain, it absorbed water and doubled in weight. The wool's natural oils provided some water resistance, but builders enhanced this by coating the sail with animal fat or pine tar, creating a relatively waterproof surface that wouldn't absorb excessive moisture. The sail's colour, often red or striped, came from natural dyes, madder root for red, woad for blue, with patterns woven directly into the fabric. Controlling this massive sail required sophisticated rigging. The yard, the horizontal spar from which the sail hung, measured approximately 13 meters long and could weigh 150 kilograms. It hung from the mast by a halyard heavy rope that could raise or lower the yard and sail. The halyard ran through a block at the masthead, then down to a windlass where multiple crew members could haul the yard up or lower it for reefing. Once raised, the yard was secured, and the sail's lower edge was controlled by sheets ropes running from the sail's lower corners to blocks near the stern. By adjusting sheet tension on either side, the steersman could angle the sail relative to the wind, allowing the ship to sail not just downwind but at angles up to 60 degrees off the wind direction. The steering mechanism, one of Viking shipbuilding's most distinctive features, consisted of a large oar-like rudder mounted on the ship's starboard side, near the stern. This side-mounted rudder, called a styrey, hung from a boss, a wooden block attached to the hull's exterior, and was controlled by a tiller running athwartships. The steersman stood or sat on the starboard side, pushing or pulling the tiller to move the rudder blade, which extended 1.5 meters below the hull. This placement on the side rather than the stern seems primitive to modern eyes, but it possessed significant advantages. The rudder could be raised in shallow water by loosening its attachment and pivoting it upward. If the rudder struck an obstacle, it would pivot backward rather than tear through the hull, and the steersman had an unobstructed view of the sail and could communicate directly with the crew. Navigation techniques remain partially mysterious because Vikings left no written sailing directions and few physical navigation instruments. They sailed primarily by dead-reckoning tracking speed and direction to calculate position. Speed was estimated by watching waves pass the hull or by throwing a floating object overboard and timing its passage from bow to stern. Direction was maintained by observing the sun's position during the day, the North Star at night, and wave patterns that remained consistent even when stars were hidden by clouds. Some evidence suggests the use of sun, compasses, wooden discs, marked with radial lines that cast shadow patterns, indicating direction and possibly sunstones, crystals like calcite that show polarized light patterns revealing the sun's position even through cloud cover. But how did they maintain course during overcast conditions that could last for days? How did they calculate latitude without instruments? The answer remains uncertain, lost when the oral tradition died. Replica voyages in the 1980s and 1990s demonstrated that experienced sailors can navigate successfully using only natural cues, wave patterns, bird behavior, watercolor, and deep accumulated knowledge of North Atlantic conditions. But modern sailors doing this know their destination from charts. Viking navigators possessed no charts, only verbal descriptions of routes learned from previous voyages. Sail due west from Norway for 2 days, then northwest until you see glaciers, then follow the coast south to the settlement. Such directions seem impossibly vague, yet they worked reliably enough that Iceland was settled by 40,000 people between 870 and 930 CE, Greenland by several thousand after 985 CE, and North America was reached, albeit temporarily, around 1000 CE. The ship's operational life depended on maintenance that began immediately after each voyage. Beaching the vessel, a task facilitated by the shallow draft and absence of a protruding keel, allowed inspection of the underwater hull. Barnacles and marine growth were scraped off using shells or stones, the exposed wood examined for damage. Cracks were caulked with tarred animal hair forced into seams using caulking irons and wooden mallets. Strakes that had worked loose were re-riveted. The entire hull was coated with pine tar, boiled to liquid consistency, and painted onto the planking while still warm. This tar treatment served multiple purposes. It sealed minor gaps, provided waterproofing, protected against marine organisms, and preserved the wood itself. A well-maintained ship required retarring annually, consuming dozens of liters of tar that had to be produced from pine stumps and roots through a slow-burning process that took days. Despite this maintenance, ships had limited lifespans. The Skuldelev ships, 5 vessels deliberately sunk in Denmark's Roskilde Fjord around 1070 CE to block the channel, show varying ages when sunk. Tree ring dating of their timbers reveals that different ships were built with wood felled decades apart, suggesting some vessels remained operational for perhaps 30 to 50 years. But this depended on usage patterns. A ship making annual North Atlantic crossings, battered by storms and saturated with salt water, might last only 15 years before requiring such extensive repairs that rebuilding made more sense. A ship used primarily for coastal trading in calmer Baltic waters could remain serviceable for twice as long. The largest known Viking ship, the Roskilde 6, excavated in 1996, demonstrates the technology's ultimate expression. 37 meters long, she required wood from approximately 300 oak trees, suggesting a forest area of 10 to 15 hectares was harvested for her construction. Building her likely took a team of specialized craftsmen, shipwrights, blacksmiths, rope makers, sail makers, an entire year, representing perhaps 8,000 hours of skilled labor. Who commanded such resources? Only chieftains or kings could marshal the workforce, materials, and organizational capacity for such projects. The ship herself became a symbol of power, a mobile fortress and political statement demonstrating her owner's ability to project force across waters. These vessels weren't just transportation, but strategic weapons that revolutionized medieval warfare. Their shallow draft allowed them to navigate rivers inaccessible to deeper-hulled ships, appearing upstream where no maritime threat was expected. Their ability to beach on any shoreline eliminated dependence on harbors, allowing raids on undefended coasts. Their speed replica vessels have achieved 9 knots under sail allowed them to strike and withdraw before defenders could organize, and their range ocean crossing capability meant nowhere was safe. From Constantinople to Newfoundland, from the Caspian Sea to North Africa, Viking ships carried warriors and traders to regions that had never seen Scandinavians, fundamentally reshaping medieval political geography. Yet for all their military success, these ships also carried farmers, livestock, tools, and supplies that established permanent settlements. The Nar, the cargo variant with higher sides and wider beam, could carry 20 to 30 tons of goods, enough for several families and their essential possessions. These vessels made Iceland and Greenland viable as settlement destinations despite being weeks from Norway. They created a diaspora that spread Norse language, law, and culture from Scandinavia to Iceland, from the Orkney Islands to Normandy, creating genetic and cultural legacies that persist a millennium later. The end of the Viking Age around 1100 CE coincided with changes in shipbuilding technology. The Hanseatic cog, a German design with straight sides, a flat bottom, and a stern-mounted rudder, proved more efficient for bulk cargo transport. Military vessels evolved toward the clinker-built but larger longships that required permanent harbours. The Norse tradition gradually merged with other European shipbuilding schools, losing its distinctive characteristics while influencing ships built from England to Russia. By 1300 CE, ships recognizable as Viking vessels had vanished from Scandinavian waters, their building techniques preserved only in the most conservative shipyards of Norway's remote fjords, where the last builders who learned the craft traditionally died in the late 19th century. What remains are the ships themselves, preserved by fortune in burial mounds or wrecks, and the replica vessels built using archaeological evidence. These reconstructions have revealed facts that written sources never could. The ships are remarkably fast, achieving speeds previously thought impossible for vessels without keels. They are remarkably seaworthy, crossing the North Atlantic with confidence in conditions that would challenge modern yachts. They are remarkably flexible, literally working with the sea in ways that seem impossible until experienced, and they are remarkably efficient, requiring smaller crews and less maintenance than period vessels of comparable size. But deeper questions remain. How did builders achieve such consistent results without standardized measurements or written specifications? What oral knowledge, transmitted master to apprentice, enabled them to shape hulls of such precision? How did they understand hydrodynamics well enough to create different optimal hull forms for different purposes without mathematical modeling? The ships themselves preserve the results of this knowledge, but not the thought processes that created it. Standing beside the Gokstad ship in Oslo's Viking Ship Museum, you can see the solution to problems carved into oak, the way the planks thin toward the top, the precisely angled stem post, the leather-wrapped rivets that sealed joints. But you cannot see the shipwright's hand testing wood with a stroke of his adze, listening to the sound it made, feeling its resistance, and knowing whether this tree would split true or cross-grain. You cannot hear the discussions between master and apprentice, the explanations of why this curve and not that one, the accumulated wisdom of generations who built ships and died while their vessels outlived them. The Viking ship represents humanity's enduring challenge, solving complex problems with limited tools and incomplete understanding, building things that work without fully knowing why they work. These ships crossed oceans 1,000 years before. Scientific hydrodynamics explained why their hull shapes were optimal. They flexed in seas centuries before. Materials science described the stress distribution that made this flexibility a strength. The builders knew, but their knowledge came through experience and intuition, not theory. What we've discovered through archaeology and reconstruction teaches us what they built. But what remains unknown, what may remain forever unknowable, is how they thought, how they decided, how they knew. The ships crossed the centuries to show us their solutions, but the problems they solved, and the reasoning that solved them, died with the last builders who worked without plans or calculations, measuring nothing, yet creating vessels. Modern engineers study with admiration they rarely express for medieval technology. In the end, perhaps that's the deepest mystery. Not how the ships worked, we can explain that now, but how minds without mathematics or material science created such sophisticated engineering. The ships survived. The knowledge that built them did not. And in that gap between artifact and understanding lies everything we've lost, and perhaps everything we're still reaching for the wisdom to solve problems we don't yet fully understand, using tools we haven't perfected, guided by intuition we cannot explain. In a longhouse somewhere in 9th century Norway, a smith heats iron in a charcoal fire burning at 1,200 degrees Celsius, watching color shifts, invisible to untrained eyes, the transition from cherry red to orange that signals the metal has reached forging temperature. He has spent 3 days smelting ore into bloom iron, another day consolidating that bloom through repeated heating and hammering, and now begins the process that will transform raw iron into a sword blade capable of cutting through chainmail, flexing without breaking, and holding an edge through battles that would destroy lesser weapons. This transformation requires no written formulas, no temperature gauges, no chemical analysis, only knowledge passed through generations, encoded in metaphor and gesture, tested against the ultimate arbiter, whether the blade kills or breaks when warriors stake their lives upon it. The iron itself begins not in forges but in bogs. Scandinavia possesses limited iron ore deposits of the type Romans mined, underground veins of hematite or magnetite requiring deep shafts and extensive labour. Instead, Norse smiths exploited bog iron, a renewable resource that forms when groundwater carries dissolved iron from surrounding soil into wetlands, where bacteria concentrate it into nodules and layers of ore, containing 30 to 50% iron by weight. These deposits regenerate a bog harvested of iron ore, will reform layers within 20 to 50 years as the slow geological process continues. This made bog iron sustainable in ways underground. Mining was not, though it meant iron remained precious. The accumulated harvest of multiple bogs required to produce enough ore for a single sword. The smelting process began by constructing a furnace, a cylindrical shaft built from clay, mixed with crushed stone and straw, standing perhaps 1.2 meters tall and 40 centimeters in diameter. The furnace was not permanent, but rebuilt for each smelt, dried slowly over several days to prevent cracking, then fired empty to harden the clay liner. On smelting day, the furnace was charged with alternating layers of charcoal and iron ore, the charcoal providing both heat and carbon monoxide that chemically reduced the iron ore, stripping oxygen from iron oxide to leave metallic iron. Bellows leather bags with wooden nozzles forced air into the furnace base, increasing temperature and accelerating the reaction. The chemistry happening inside that clay cylinder was complex enough that modern metallurgists struggle to replicate it reliably. Iron melts at 1538 degrees Celsius, but the furnace reached only 1200 to 1300 degrees hot enough to make iron plastic and workable but not liquid. This temperature range was critical. If too cool, the chemical reduction wouldn't complete, leaving iron oxide mixed with metal. If too hot, the iron would melt and absorb excessive carbon from the charcoal, becoming brittle cast iron rather than workable wrought iron. The smith maintained proper temperature through sound. The roar of the fire, the pitch of bellows exhaling, the crackle of charcoal consuming itself and through colour, peering through openings in the furnace wall to judge the glow of materials inside. After 8 to 12 hours of continuous operation, consuming perhaps 50 kilograms of charcoal and 20 kilograms of ore, the furnace was broken open to reveal the bloom, a spongy mass of iron mixed with slag, silicate impurities from the ore that hadn't melted away. This bloom might weigh 3 to 5 kilograms, meaning efficiency was roughly 15 to 25%. Most of the ore's iron remained locked in the slag. The bloom, still glowing orange, was immediately transferred to an anvil where the smith hammered it repeatedly, each blow forcing slag out through the iron's porous structure. This consolidation continued through multiple reheating and hammering cycles, gradually transforming the spongy bloom into dense bar stock, though even after extensive work, the iron retained microscopic slag inclusions that modern analysis reveals in every artifact. This consolidated iron, what metallurgists call wrought iron, contains less than 0.1% carbon, making it tough and malleable but too soft to hold a sharp edge. Creating steel, iron with 0.5 to 1.5% carbon, required controlled addition of carbon atoms into the iron's crystalline structure. Vikings achieved this through carburization, heating iron bars packed in crushed bone, charcoal, or leather in a sealed clay container for hours or days. Carbon from the organic material migrated into the iron's surface, creating a hardened layer that could be forged into cutting edges. The depth of this carburized layer depended on temperature and time. Hotter and longer meant deeper penetration, but also greater risk of excessive carbon absorption that would make the steel brittle. Pattern welding, perhaps the most sophisticated technique in the Viking smith's repertoire, created blades from multiple pieces of iron and steel twisted, folded, and forge-welded together. The process began with several bars of iron and carburized steel, stacked and heated to welding temperature, approximately 1100 degrees Celsius, where the metals become sticky and can be hammered into a single piece. This required precise temperature control. Too cool, and the pieces wouldn't bond. Too hot and oxidation would prevent welding. The smith withdrew the bundled bars and hammered them flat, the impact forcing out oxide scale while bonding the layers. This flattened bundle was then cut in half, the halves stacked, and the process repeated heating, hammering, folding perhaps 7 to 15 times. Each folding doubled the layer count. 7 folds created 128 layers, 10 folds produced 1024 layers, 15 folds resulted in 32,768 layers, each one thinner than paper, visible in finished blades as flowing patterns resembling wood grain or water ripples. These patterns weren't merely decorative, but indicated the blade's internal structure, regions of alternating hard steel and soft iron that combined the steel's ability to hold an edge with the iron's flexibility and Toughness. A blade that was entirely hard steel would shatter on impact, with bone or another weapon. A blade of pure soft iron would bend and dull immediately. The pattern-welded combination provided optimal performance, though creating it required days of work and generated enormous waste. Perhaps half the material oxidized away or flaked off as scale during repeated heating. The central core of the finest swords consisted of this pattern-welded material, providing flexibility and resilience. The blade's edges were different strips of high-carbon steel, forge-welded onto either side of the core, creating the actual cutting surfaces. This composite construction placed hard, sharp steel precisely where needed, while keeping the blade's core tough and flexible. Archaeological analysis of surviving Viking swords reveals this three-part structure. A twisted core visible in X-rays, with edge strips of different composition showing higher carbon content when examined through microscopy. Modern bladesmiths attempting to recreate this process report that creating a single sword requires approximately 100 to 200 hours of work, and numerous attempts fail. Layers don't bond properly. Inclusions create weak points, or carbon distribution becomes uneven. Tempering, the final heat treatment, transformed brittle, hardened steel into resilient, functional material. After grinding and shaping the blade to its final form, the smith heated it to approximately 800 degrees Celsius, identified by a medium red glow in dim lighting, then plunged it into liquid. The quench medium water, oil, urine, or brine cooled the steel rapidly, trapping carbon atoms in a stressed crystalline structure called martensite that was extremely hard but also brittle. A blade in this state would shatter like glass if struck. Tempering relieved these internal stresses by reheating the blade to 200 to 300 degrees Celsius. Temperatures identified by oxide colors appearing on polished steel, progressing from pale yellow through purple to blue as temperature increased. This tempering temperature was critical and varied, depending on the blade's intended use. Swords required flexibility, so they were tempered at higher temperatures that sacrificed maximum hardness for toughness. Axes, which struck harder blows and needed to bite deeply into wood or bone, were tempered at lower temperatures to maintain hardness despite increased brittleness. Knives intended for cutting leather or carving wood received different treatment than fighting knives that might strike metal rivets or bone. Each tool required different properties, and the smith needed to know, through experience, exactly which color indicated optimal tempering for each application. This knowledge was proprietary, a smith's competitive advantage in an economy where reputation determined whether chieftains commissioned work or sought competitors. The social position of smiths reveals how societies valued their work. In Norse mythology, the dwarves' master craftsmen working underground forged the gods' greatest treasures. Thor's hammer, Mjolnir, Odin's spear, Gungnir, Freya's ship that could fold into a pocket. These myths reflected reality. Exceptional smiths achieved fame that outlived them, their names preserved in sagas, while ordinary warriors were forgotten. The sword Ulfbert, a name that appears on approximately 170 blades found across Europe, might have been a smith's signature, or perhaps a workshop brand. These Ulfbert swords, produced primarily between 900 and 1100 CE, contained steel of remarkably consistent quality, suggesting centralized production by specialized smiths with access to superior ore or advanced techniques. Recent analysis shows their carbon content averages 0.8% optimal for swords, while contemporary blades often contain half that amount or show irregular carbon distribution. But where did the knowledge to achieve such consistency originate? Iron smelting began in the Near East around 1200 BCE, spreading to Europe by 800 BCE. By the Roman period, smiths understood carburization and quenching, but pattern welding appears to be a uniquely Northern European innovation, appearing around 200 CE and reaching peak sophistication during the Viking Age. Why did this technique develop here and not in the Mediterranean, where iron technology was more advanced in other respects? The answer remains unclear. Some scholars suggest pattern welding compensated for inferior ore quality, creating homogeneous material from inconsistent iron sources. Others argue it served primarily decorative purposes, the flowing patterns signaling quality to customers who couldn't assess metallurgy directly. Archaeological evidence suggests both explanations contain partial truth. Analysis of Roman period pattern-welded blades shows they were indeed stronger and more flexible than contemporary single-piece blades, supporting the functional interpretation. Yet Viking Age smiths continued pattern welding even after developing crucible steel techniques that could produce homogeneous high-carbon steel from a single smelting operation, suggesting aesthetic considerations mattered as much as performance. The patterns themselves varied by region and period. Early blades show simple twisted patterns. Later ones display elaborate herringbone or spiral designs that required additional manipulation of the twisted bars before final welding. This elaboration suggests fashion and status signaling influenced design as much as purely functional concerns. The transition from bloom iron to crucible steel represents another knowledge transfer whose mechanism remains mysterious. By 900 CE, some Viking smiths had access to steel produced through crucible process, heating iron with carbon sources in sealed containers for days, creating homogeneous steel of consistent quality. This technique originated in India around 400 CE, and by Islamic period had spread to the Middle East, where Damascus became famous for swords made from wootz steel, a crucible steel variant. But how did this knowledge reach Scandinavia? Vikings traded with Constantinople, which connected to Islamic trade networks. They also raided and sometimes settled in regions where crucible steel was known. Perhaps captured smiths taught their captors. Perhaps traded steel ingots were reverse engineered through examination and experimentation. Perhaps written descriptions, transmitted through intermediaries, provided enough information for skilled smiths to recreate the process. We have the artifact steel that isotopic analysis confirms came from Middle Eastern sources, and steel that chemical analysis shows was produced in Scandinavia using techniques that originated elsewhere, but the transmission mechanism remains unrecorded. Cutting tests performed on replica Viking swords, forged using reconstructed techniques, to reveal performance that explains their effectiveness in battle. A properly made pattern-welded sword can cut through a rolled grass mat soaked in water, a test simulating resistance of flesh and muscle in a single stroke, then strike an iron helmet hard enough to dent it without damaging the blade. The same sword can flex 30 degrees from straight without taking permanent set, returning to true when pressure is released. This combination of sharpness, strength, and flexibility made Viking swords among history's most effective hand weapons, superior to most contemporary blades, and not definitively surpassed until the development of spring, steel, and modern heat treatment in the 19th century. Yet these high-quality swords were rare. Most warriors carried simpler blades, single-piece constructions without pattern welding, perhaps with only the edge hardened through quenching. A substantial warrior might own a single good sword, acquired through inheritance or as a gift from a patron, maintained carefully and passed to the next generation. The finest swords received names Legbiter, Skull Splitter, and appeared in sagas as characters in their own right, their lineage tracked as carefully as human genealogies. This naming tradition reflects the sword's value, which in monetary terms equaled several years of an ordinary farmer's income, and in practical terms might mean the difference between survival and death in combat. Axes, more common than swords because simpler to produce, nonetheless showed sophistication in their construction. The Dane axe, a weapon with a blade measuring approximately 25 centimeters across, mounted on a haft up to 1.8 meters long, could cleave through shields and helmets with crushing force. Yet the blade itself weighed only about half a kilogram, much lighter than swords, because axes required sharp edges only at the bit, while the rest of the head could be soft iron. Some axes were forge welded from multiple pieces, soft iron forming the socket and body, with a steel bit inserted and forge welded between them. This economized steel, placing it only where hardness was essential, while keeping the rest of the head tough and resistant to shattering. Spears, the most common Viking weapon, ranged from simple socketed iron points on wooden shafts to elaborate pattern-welded heads with wings or barbs. The socket, the hollow cone that fit over the wooden shaft, required the smith to forge a flat piece of iron into a tube, overlapping the edges and forge welding them. This operation sounds simple, but demanded precise control. The overlap had to be wide enough to create a strong weld, but not so wide that excess material created internal irregularities. The blade itself might be pattern welded in expensive versions, or simply shaped from a single piece of steel in utilitarian models. Archaeological excavations reveal that burial mound weapons, interred with wealthy individuals, show much more elaborate construction than weapons found in common graves or battle sites, suggesting social stratification extended even to weapon quality. The decoration of weapons reveals another dimension of the smith's art. Silver or copper wire could be hammered into grooves, filed into sword hilts, creating intricate geometric or zoomorphic patterns. Some hilts were plated with precious metals or decorated with cloisonné cells of metal filled with enamel or glass. These decorative techniques required cooperation between smiths and specialized craftsmen, with the blacksmith creating the basic form and the goldsmith or jeweler adding embellishment. The Sutton Hoo sword, though Anglo-Saxon rather than Viking, demonstrates the pinnacle of this art. A blade with pattern-welded core, gold hilt fittings decorated with garnets, and a scabbard with elaborate metalwork. Creating such a weapon required coordinating multiple specialists, each contributing months of work, resulting in an object whose value derived as much from artistry as functionality. The smith's workshop contained specialized tools whose forms remained essentially unchanged from Roman times through the medieval period. The anvil, a heavy block of hardened iron or steel, weighing 50 to 100 kilograms, provided a work surface that could withstand thousands of hammer blows without deforming. Hammers varied from small finishing hammers weighing less than a kilogram to sledges exceeding 5 kilograms, used for heavy forging or when apprentices struck metal held by the master smith. Tongs in dozens of shapes gripped different-sized workpieces, their jaws custom-shaped for specific tasks. Files, rasps, and grinding stones refined shapes and smoothed surfaces. A hardie, a chisel with a square shank that fit into the anvil, allowed the smith to cut hot metal by hammering the workpiece against the hardie's cutting edge. The fuel for the forged charcoal required its own specialized production. Charcoal burners felled trees, cut them into pieces, and stacked them in conical mounds covered with turf and clay. These mounds were ignited and allowed to smoulder for days, the limited oxygen supply preventing complete combustion and converting wood into charcoal, nearly pure carbon with energy density triple that of wood. A single sword's production consumed approximately 50 kilograms of charcoal, representing perhaps 200 kilograms of original wood. This massive fuel requirement meant smithies located near forests, and successful smiths needed either woodland access rights or sufficient wealth to purchase charcoal in bulk. The decline of pattern welding after 1100 CE coincided with several changes: increased availability of higher quality iron ore from Central European mines, development of larger furnaces capable of producing steel directly rather than requiring carburization, and perhaps most significantly, the feudal system's concentration of weapon production in larger workshops where specialized smiths produced components that were assembled elsewhere. The intimate knowledge of individual smiths, working alone or with one or two apprentices, gave way to more industrial processes, where standardization and volume production mattered more than individual craftsmanship. By 1300 CE, pattern welding had essentially ceased, remembered in sagas but no longer practiced, its techniques surviving only fragmentarily until modern experimental archaeologists began reconstructing them in the late 20th century. What those reconstructions revealed startled modern metallurgists. The Viking smiths, working without thermometers, microscopes, or metallurgical theory, nonetheless achieved results that meet or exceed what modern industrial processes produce. The pattern-welded blades, when analyzed, show layer bonding of remarkable quality. Welding defects are rare, carbon distribution is relatively even, and the interface between steel and iron layers is microscopically clean. Achieving this required temperature control within approximately 50 degrees Celsius across hours of repeated heating in a fuel whose temperature varied with airflow and charcoal quality. Modern smiths, even when attempting to recreate these techniques using period tools, report high failure rates perhaps. 1 in 3 or 1 in 4 blades develops critical flaws during forging. This success rate suggests that Viking smiths operated at an extraordinary skill level, their knowledge of materials and processes deep enough to compensate for lack of instrumentation through direct sensory observation and intuitive understanding. They knew how different ores smelled when smelting, which smells indicated proper reduction and which signaled problems. They knew the sound of properly carburized steel when struck a ringing tone that differed from the duller sound of soft iron. They knew the feel of metal at forging temperature, the resistance it offered to the hammer, the way it moved under blows, the texture of its surface when examined in dim firelight. This embodied knowledge information, stored not in writing but in trained hands and educated senses, disappears when transmission breaks. The last smiths who learned these techniques traditionally, by years of apprenticeship under master craftsmen who themselves learned through apprenticeship, died in the 19th century. Modern practitioners learning from books and archaeological evidence achieve impressive results, but they acknowledge gaps, details that seem simple but prove crucial, techniques that sources don't mention because they were too obvious to record, judgment calls that become instinctive only after years of experience. The artifacts survived. The knowledge that created them partially survived. But something essential was lost in the gap between tradition and reconstruction. Perhaps the deepest mystery isn't how they worked. Metal, we can analyze that, but how they knew to work it these particular ways. Pattern welding isn't intuitive. Nothing about forging iron suggests that twisting multiple bars together, folding them repeatedly, then welding steel edges onto the result, would create superior blades. Yet somehow, over centuries of experimentation, smiths discovered this technique and refined it to high art. How many failed experiments preceded success? How many smiths died in fires, or from lung disease caused by forge smoke, or simply from the physical exhaustion of working in 1,200-degree heat? The artifacts preserve successes, but the failures, the broken blades, the cracked welds, the experiments that didn't work, corroded away or were recycled, leaving no record. What we see in museums are the survivors' blades that worked so well they were preserved, passed down, buried with honored dead. These represent the peak of achievement, not typical performance. For every elaborately pattern-welded sword in a museum, a dozen simpler blades saw service and wore out. For every smith whose work survives in collections, hundreds of competent craftsmen produced adequate but unremarkable tools that corroded away centuries ago. The archaeological record preserves excellence and condemns mediocrity to invisibility, giving us a skewed view that emphasizes exceptional achievement while understating the skill required even for ordinary competence. Standing before a Viking sword in a museum display case, seeing the flowing patterns in the blade, the elegant lines of the hilt, the balance that allowed it to function as extension of a warrior's arm, You're seeing the end point of a process that began with trees cut for charcoal, ore scraped from bogs, countless hours at the forge, and knowledge accumulated over generations. But you cannot see the smith's squinting assessment of the blade's colour in firelight, cannot hear the hammer's rhythmic percussion, cannot smell the acrid smoke, or feel the heat that made work possible only for short intervals, before the smith had to step outside to cool down. The sword crosses centuries to show us what was achieved, but how it was achieved, the moment-by-moment decisions, the corrections of errors, the improvisations when materials didn't behave as expected, those died with the smiths. We have their products. We can analyze the metallurgy, measure the dimensions, recreate the appearance, but the thinking, the problem-solving, the accumulated wisdom of a lifetime spent manipulating metal that remains partially hidden, preserved imperfectly in artifacts that answer what and when, but leave why and how, as questions we're still learning to ask correctly. In 870 CE, a Norse ship departed from western Norway carrying families, livestock, and everything required to establish a new life on an island no one aboard had ever seen. The destination, Iceland, lay roughly 1,000 kilometers to the northwest across open ocean, where storms could appear with hours of warning and fog could obscure the sky for days. The navigator possessed no compass, no sextant, no charts showing Iceland's position. Yet somehow, after perhaps a week at sea, the ship made landfall on Iceland's eastern coast, close enough to intended destination that the settlers could establish their farm within days of arrival. This feat was repeated thousands of times over 60 years, as Iceland's population grew from 0 to 40,000 people, each ship finding a destination smaller than many modern cities, across an ocean that has swallowed countless vessels before and since. How they accomplished this remains one of maritime history's most persistent mysteries. The Vikings left no navigation manuals, no written sailing directions, no instruments that can definitively be identified as navigation tools. What survives are scattered references in sagas to navigation techniques, a few enigmatic artifacts that might have been used for wayfinding, and the undeniable evidence that they succeeded reaching Iceland, Greenland, and North America with sufficient reliability to establish permanent settlements. Modern sailors attempting to recreate these voyages using period technology report success rates that approach Viking reliability, but acknowledge they navigate with advantages the Norse lacked: knowledge of their destination's location, modern weather forecasting, and rescue infrastructure if things go wrong. Strip away those advantages, and the achievement becomes almost incomprehensible. The journey to Iceland from Norway begins with understanding the departure point. Most settlers likely left from western Norway, from fjords around Bergen or further north near Trondheim, where tradition claimed Iceland's first discoverers originated. The initial leg of the voyage ran northwest, following the Norwegian coast until reaching the Shetland Islands, roughly 350 kilometers, that could be completed in 2 days of favourable sailing. This coastal passage presented minimal navigation challenges. Land remained visible on the starboard side, and even in fog, the sound of waves breaking on shore provided directional guidance. The Shetlands offered the last reliable resupply point, fresh water, and shelter for repairs before the open ocean crossing. From the Shetlands to the Faroe Islands measured approximately 340 kilometers, a passage of perhaps 36 hours in good conditions. This segment introduced the first real navigation challenge, leaving sight of land and sailing northwest across open water, with no visible landmarks, until the Faroes appeared on the horizon. The navigator needed to maintain consistent heading, despite winds that rarely blow steadily from one direction, currents that push vessels off course, and the ship's tendency to make leeway sliding sideways through the water when sailing at an angle to the wind. Arrive too far south, and you miss the islands entirely, continuing into open Atlantic. Too far north, and you reach them after wasting time and distance, potentially exhausting food and water supplies. The sun provided primary directional reference during daylight. At northern latitudes during summer, when most Viking voyages occurred, the sun remains visible nearly 24 hours daily, its path arcing across the southern sky. At solar noon, when the sun reaches its highest point, it lies due south, providing a reliable directional fix. But solar noon lasts only a moment, and the rest of the day, the sun's azimuth, its compass bearing, changes constantly as it appears to move across the sky. An experienced navigator learned the sun's azimuth at different times of day for different seasons, internalizing a mental model of solar motion that allowed dead reckoning. The sun stands there at mid-morning in late June, so that direction is northwest, which means we're heading correctly. Night navigation relied on stars, particularly Polaris, the North Star, which sits almost directly above Earth's North Pole and appears stationary while other stars wheel around it. Polaris allows direct determination of north, and its altitude above the horizon equals the observer's latitude. A navigator in western Norway, at approximately 61 degrees north latitude, sees Polaris 61 degrees above the northern horizon. Arriving in Iceland, at roughly 65 degrees north, Polaris appears 4 degrees higher, roughly 8 sun-widths, since the sun's angular diameter is approximately half a degree. This change in Polaris's altitude provided confirmation of latitude, allowing navigators to verify they had sailed far enough north before turning west to run down Iceland's latitude until making landfall. But what about overcast conditions, when neither sun nor stars were visible? The North Atlantic is notorious for extended periods of cloud cover, fog banks that reduce visibility to meters, and storms that obscure the sky entirely. Saga accounts mention sunstones, mysterious crystals that could reveal the sun's position even through clouds, but provide no technical details about how they worked or what material they were made from. Modern researchers have proposed that Vikings used calcite crystals, which exhibit a property called birefringence. When viewed through calcite, light becomes polarized, and by rotating the crystal and observing brightness patterns, the sun's direction can be determined even when the sun itself is hidden by clouds or just below the horizon. Experimental tests using calcite crystals in the 1960s through the present day show this technique works under laboratory conditions. But does it work on a pitching, rolling ship deck? How accurately? And most critically, have any calcite crystals been found in Viking archaeological contexts in circumstances suggesting navigational use? The answer to the last question remains ambiguous. A calcite crystal was found near a navigational device in a 16th century ship, centuries after the Viking Age, but no definitive Viking period sunstone has been identified. The technique remains plausible but unproven, an elegant solution that may or may not represent historical reality. Wave patterns provided another navigational input, particularly important during overcast conditions. Ocean waves are created by wind, but once formed, they propagate across vast distances as swells regular, rolling undulations that maintain consistent direction even after the wind that created them has stopped. An experienced sailor learns to recognize these swells, noting their direction even when steering by other means, and can use them as a compass when other references fail. Icelandic sources mention navigators using wave direction to maintain course, and modern sailors confirm this works during extended fog. Waves provide the only reliable directional reference when sun and stars are invisible. But reading wave patterns requires distinguishing between multiple overlapping wave trains, wind waves from local weather, swells from distant storms, reflected waves bouncing off distant shores, and interpreting which set represents the dominant swell that can be used for navigation. This skill comes only through years of observation, learning to feel the boat's motion, to see patterns in apparently chaotic seas, to recognize the deep, slow rhythm of swells beneath the chop of surface waves. Modern sailors attempting this report that after days of practice, they can detect swells they previously couldn't perceive, suggesting this ability develops through training rather than being immediately accessible to inexperienced observers. Seabirds provided proximity indicators for land. Certain species fulmars, gannets, puffins feed at sea but nest on land, venturing only limited distances from their colonies. Observing these birds flying toward a particular direction at evening suggests land lies that way, often before it becomes visible. Similarly, clouds that form over land but not over open ocean create distinctive patterns. A stationary cloud bank on the horizon likely indicates an island beneath it. The color of water changes near shore, shifting from deep blue to green or brown as depth decreases and bottom material becomes visible. Even the smell changes. Land smells different from open ocean, the scent of vegetation and earth carrying downwind for surprising distances. But how does a navigator integrate all these inputs? Sun position, star altitude, wave direction, bird behavior, cloud patterns into a reliable position estimate. Modern navigation uses mathematics. Speed multiplied by time equals distance traveled, with trigonometry to account for course changes. Did Vikings perform these calculations? Saga references to navigation use no numbers, suggesting mathematical computation wasn't the primary method. Instead, navigators likely maintained what modern psychologists call situational awareness, a continuous mental model of position built from multiple inputs, updated constantly as new information arrived, providing an intuitive sense of location rather than calculated coordinates. This intuitive navigation requires extraordinary memory and pattern recognition. The navigator must remember the departure point's latitude, the intended destination's latitude, the distance between them, and how these relate to observable phenomena. They must recognize when the ship has been pushed off course by currents or wind, estimate how far off, and adjust accordingly. They must maintain this mental model through days or weeks at sea, through sleep deprivation, through storms that make observation difficult or impossible. And they must do all this while also managing the ship, adjusting sail, organizing the crew, monitoring weather, because on small vessels the navigator was usually also the helmsman or captain, not a dedicated specialist. The sailing directions preserved in later medieval texts, though written centuries after the Viking Age, likely preserve earlier oral traditions. These directions read like, from Hernar in Norway, sail west to Hvarf in Greenland, passing north of Shetland so you can just see it in clear weather, and south of the Faroes so the sea appears halfway up the mountains, and south of Iceland so you see birds and whales from there. These instructions provide latitude references. Passing specific distances, north or south of landmarks, allows the navigator to maintain approximately constant latitude and include expected phenomena at different stages of the journey. Seeing birds and whales from there means Iceland lies close enough that its seabird populations extend to your position, providing confirmation you're on the correct route. But notice what these directions don't include: distances in any measurable unit. They don't say, sail 700 kilometers west, because Vikings had no way to measure distances at sea. They might estimate travel time 3 days sailing, but this varied with wind conditions, sea state, and the specific ship's speed. 2 ships following identical routes might take 2 days or 5 days depending on weather, so time provided only rough guidance. The directions instead use geographic, relationships passing north of this, south of that, until you see these signs creating a sequence of checkpoints that confirmed position without requiring distance measurement. Speed estimation at sea without instruments presents challenges modern sailors rarely consider. Vikings likely used 2 techniques. First, watching objects float past the hull, throw a piece of wood overboard at the bow, walk aft while counting, and note where along the ship's length it passes when the count reaches a certain number. This gives relative speed. The ship is moving 3 paces per 10 count, though translating this into actual speed requires knowing the relationship between paces, counts, and distance, which may have been internalized rather than explicitly calculated. Second, the sound and feel of water moving past the hull changes with speed. An experienced sailor learns to estimate speed by listening and feeling, though this provides only rough approximation. Current understanding suggests Vikings navigated primarily by latitude sailing, reaching the correct latitude, then sailing east or west along that parallel until reaching the destination. This technique, still used by sailors before reliable longitude measurement became possible in the 18th century, works because latitude can be determined relatively easily through solar or stellar altitude, while longitude requires accurate timekeeping that wasn't available. To reach Iceland from Norway, the navigator would sail northwest until Polaris's altitude indicated they had reached Iceland's latitude, then turn west and sail along that parallel until sighting land. This method is forgiving of east-west errors. Arrive too far east or west, and you still hit Iceland's 500-kilometer wide coast, but intolerant of north-south errors miss the latitude, and you sail past Iceland into empty ocean. Yet this raises questions about Iceland's initial discovery. If the first explorers traditionally identified as Nadod, Garðar, and Floki in the 860s CE were blown off course or exploring randomly, how did they find Iceland? And having found it, how did they navigate back to Norway to report the discovery? The sagas provide conflicting accounts. One claims Nadod was blown off course while sailing to the Faroe Islands and accidentally discovered Iceland. Another says Garðar deliberately searched for land, rumoured to exist in the northwest. A third describes Floki using ravens released at sea, which circled and then flew northwest, leading him to land a technique that sounds mythical but actually makes practical sense, since ravens fly toward nearest land when released far from shore. Perhaps Iceland's discovery involved luck combined with deliberate exploration. Ships blown off course would encounter land masses and could note their approximate direction and distance from known locations. Subsequent voyages could deliberately sail in that direction, narrowing the search area with each attempt. Once Iceland was located, its position relative to Norway could be described in terms of sun angles, star positions, and sailing time, allowing others to repeat the journey. This gradual refinement from vague land exists somewhere northwest to precise sailing directions occurs across multiple voyages, each adding detail and correcting errors from previous attempts. Archaeological evidence from Iceland's settlement period shows farms scattered across the entire island, suggesting arriving ships made landfall at many different points around the coast. This distribution implies navigation accuracy varied considerably. Some ships hit their intended destination, others arrived hundreds of kilometers off target but close enough to establish settlements anyway. Iceland's size made it a forgiving target. A navigation error that would cause complete failure when seeking a smaller island still resulted in successful landfall somewhere on Iceland's extensive coastline. The progression from Iceland to Greenland to North America shows increasing sophistication in navigation over time. Eric the Red's voyage to Greenland in 985 CE followed the latitude sailing technique from Iceland, but Greenland lies much further west, approximately 450 nautical miles versus the 600 from Norway to Iceland, and its southern tip extends to lower latitudes, requiring course changes mid-voyage. Leif Erikson's voyage to North America around 1000 CE covered even greater distances across more open ocean. That these later voyages succeeded suggests accumulated experience, improved navigation techniques, though written sources don't explicitly describe what those improvements were. The possibility of using wooden navigation instruments, sun compasses, or bearing dials has generated considerable scholarly debate. Several wooden discs with radial markings have been found in Viking contexts, most famously a fragment from Uunartok in Greenland that some researchers interpret as a sun compass. The device theoretically works by casting a shadow from a central gnomon, a vertical pin, onto the marked dial, with the shadow's direction indicating the sun's azimuth. By marking the shadow's position at solar noon, when it points due north, the navigator creates a reference line. Subsequent observations comparing the shadow's position to this reference reveal compass direction, but problems complicate this interpretation. The Uunartok fragment shows markings that don't align with any obvious astronomical pattern. It was found near a monastery, not a ship, in a context dating to the late medieval period, well after the Viking Age ended, and experimental replications report difficulties using such devices on moving ships. The gnomon's shadow becomes blurred and indistinct in less than perfect conditions, and the device requires precise leveling to work accurately. These objections haven't prevented enthusiasts from constructing replicas and testing them at sea, with mixed results. Some report useful navigational information, others find the devices impractical. The question remains unresolved. What seems certain is that Vikings did not navigate using dead reckoning in the modern sense, continuously calculating position from speed and course. The mathematical complexity of such calculations, combined with the difficulty of measuring speed and the cumulative errors from waves and currents constantly pushing the ship off its ideal course, would make pure dead reckoning impractical without computational tools Vikings didn't possess. Instead, they likely practiced what might be called associative navigation, building a mental map of relationships between observable phenomena and geographic locations, using this map to recognize where they were and adjust course accordingly. This type of navigation, still practiced by Pacific Islanders until the 20th century and documented by anthropologists, treats the ocean not as featureless void but as a landscape filled with signs and patterns. Pacific navigators learn star paths, sequences of stars that rise over specific islands, creating a mental framework where sailing toward the rising point of star X means heading toward island Y. They recognize swells that wrap around islands in distinctive patterns, identify zones where certain bird species appear, and use all these inputs to maintain situational awareness across thousands of kilometers of open ocean. Viking navigation likely employed similar principles, adapted to North Atlantic conditions and the specific phenomena available there. But if this knowledge was transmitted orally through apprenticeship and direct experience, how much was lost when the tradition died? Iceland's settlement concluded by 930 CE, Greenland's by around 1000 CE. After 1000 CE, voyages to North America ceased, and within a century or two, even the Greenland route became downed. Less frequently travelled as Norway focused eastward toward the Baltic and Mediterranean. The master navigators who made multiple Atlantic crossings died, and their knowledge died with them unless successfully transmitted to apprentices who themselves made such voyages. By the 1300s, when European navigation began adopting magnetic compasses from China and astrolabes from the Islamic world, the indigenous Norse navigation tradition had largely faded, replaced by newer technologies that provided more reliable results with less training. What we've reconstructed through experimental archaeology and analysis of saga references provides a plausible picture of Viking navigation. But plausibility isn't certainty. We know they succeeded, the settlements prove it. We know roughly what information sources were available to them: sun, stars, waves, birds, all of which are documented in later sources. We can demonstrate that navigation using only these sources is possible. Modern replica voyages confirm this. But we don't know exactly what techniques they used, how they integrated different information sources, what mental models they employed, or how they taught these skills to the next generation. Consider the simplest question: how did a young man become a navigator? Did he apprentice to an experienced navigator making multiple voyages as crew before being entrusted with navigation responsibilities. Did he learn through formal instruction, memorizing sailing directions and star positions, or did he accumulate knowledge gradually over years of coastal sailing, eventually attempting longer passages as his understanding deepened? The sagas mention navigators by name, suggesting it was a recognized specialty, but provide no details about training or qualification. Some historical evidence suggests navigation knowledge was considered proprietary, valuable enough that navigators guarded it carefully, teaching only selected students. But this interpretation comes from later periods and might not apply to the Viking Age. The Christian conversion of Scandinavia in the 11th century may have disrupted navigation knowledge transmission more than political or economic changes. The Church promoted literacy and written record-keeping, but focused on religious texts rather than practical seafaring knowledge. Oral traditions, including navigation techniques, weren't considered worth recording by Christian scribes, who viewed them as pagan knowledge or simple craft skills beneath scholarly attention. By the time anyone thought to write down sailing directions, centuries had passed, and what was recorded represented a degraded version of earlier knowledge, simplified and partially forgotten. Modern GPS navigation allows position determination to within meters anywhere on Earth, rendering traditional navigation techniques obsolete for practical purposes. Yet enthusiasts still practice celestial navigation using sextants, and a small community attempts to reconstruct and preserve Viking navigation methods. These practitioners report that the techniques work, but require extended practice to develop the observational skills and intuitive understanding that would have been second nature to Viking navigators. Reading wave patterns, estimating latitude from Polaris altitude, integrating multiple weak information sources into a coherent position, estimate these skills, develop slowly, and most modern sailors find GPS more convenient and reliable than mastering traditional techniques. What's lost in that convenience is the intimate connection between navigator and environment that traditional navigation required. A GPS user knows their position as abstract coordinates, but may not notice the waves, the birds, the cloud patterns, or the watercolor. A traditional navigator must remain constantly aware of these phenomena, building a holistic understanding of the maritime environment. This awareness extends beyond navigation. It includes weather prediction, knowledge of sea conditions, understanding of how the ship responds to different situations, creating a relationship between sailor and sea that instrument-based navigation doesn't require. Standing on Iceland's eastern coast, looking west across the North Atlantic toward Greenland's invisible mountains 800 kilometers distant, you can imagine a ship appearing from the horizon, a square sail marking its approach, the hull's clinker planking catching sunlight, 30 people aboard searching for the land their navigator promised lay ahead. You can imagine their relief when Iceland's peaks appeared, confirming that all the observations, all the star sightings, all the wave reading and bird watching had worked. But you cannot imagine what they saw that you don't, what patterns in the waves spoke to them, what the sky's color told them about distance to land, what they smelled on the wind that suggested proximity to shore. The ships survived, preserved in bogs and burial mounds. The settlement survived, their ruins still visible across Iceland's landscape. But the knowledge that guided ships across oceans, the accumulated wisdom of generations who read the sea like a language that survived only fragmentarily, enough to know it existed, but not enough to fully reconstruct it. We have the results of their navigation. We can demonstrate that successful navigation was possible using period information sources, but the experience of navigating the moment-by-moment observations and decisions, the confidence or uncertainty they felt, the mental processes that integrated fragmentary inputs into reliable guidance that remains hidden, preserved imperfectly in artifacts and accounts that answer some questions while raising others we're still learning to formulate. In the Longhouses' dimly lit corner, a woman stands before a vertical loom, measuring 2 meters tall and 1.5 meters wide. Its warp threads the vertical fibers that form the fabric's foundation, held taut by clay weights suspended from the bottom. She has been weaving this piece for 3 weeks, working several hours daily when other responsibilities permit, and when finished in another week, she will have produced roughly 10 meters of wool fabric 30 centimeters wide. This cloth represents approximately 120 hours of her labor, but that accounts only for the weaving itself, not the months spent shearing sheep, cleaning wool, spinning thread, and preparing the loom. A complete outfit for one person required roughly 4 such panels, meaning a single set of clothing represented nearly 500 hours of work. In a society without ready-made garments or textile factories, clothing was wealth, measured not in coins but in the thousands of hours embedded in every tunic and cloak. Textile production begins not with spinning or weaving but with sheep specifically, breeds developed over centuries for wool rather than meat. Archaeological analysis of Viking-age sheep remains shows they were significantly smaller than modern breeds, weighing perhaps 30 to 40 kilograms rather than 60 to 80, but they produced wool with characteristics particularly suited to Norse needs. The fleece contained 2 distinct fiber types, a long coarse outer coat called tog and a short fine undercoat called vel. This dual coat structure, preserved in a few heritage breeds like modern Icelandic sheep, provided fibers for different purposes. The long tog fibers for hard-wearing outer garments and sailcloth, the fine thel for softer undergarments and high-quality fabrics. Shearing happened once annually in late spring, using iron shears that resembled modern scissors but operated through spring tension rather than a pivot screw. Squeezing the handles together brought the blades together, and releasing them allowed the spring to push them apart. The shearer worked systematically across the sheep's body, cutting the fleece away in large sections that would be processed as units. A skilled shearer could process 20 to 30 sheep per day, though speed had to be balanced against the risk of cutting the sheep's skin or leaving wool attached. The resulting fleece, still greasy with lanolin and embedded with dirt, vegetable matter and dried manure, weighed approximately 2 to 3 kilograms per sheep. Cleaning this raw fleece required multiple steps that removed contaminants while preserving enough lanolin to keep fibers supple and somewhat water-resistant. The first step involved simply opening the fleece and shaking it vigorously, dislodging large debris. Then came washing not in hot water with soap, which would strip all oils and make fibers brittle, but in lukewarm water with perhaps urine as a weak alkali agent that helped dissolve dirt while leaving some lanolin intact. The Romans used fermented urine as a textile processing agent, and evidence suggests Vikings did likewise, collecting it in dedicated vessels and allowing it to age until its ammonia content increased. After washing and rinsing, the fleece was spread on grass or hung on frames to dry over several days. The dried fleece then underwent carding or combing to align fibers and remove remaining debris. For fine fibers, wool carders' flat paddles studded with bent wire teeth pulled fibers apart, aligned them, and removed short, broken fibers that would create weak points in thread. For long fibers, intended for sturdy fabrics, wool combs, large toothed tools mounted to posts or held between knees, pulled fibers straight and sorted them by length. This preparation stage separated Viking textile production from simpler cloth-making traditions. Careful fiber preparation produced stronger, more uniform thread that wove into better fabric. Spinning, converting loose wool fibers into continuous thread required a spindle, a tool so simple that describing it makes its operation sound effortless, yet mastering it demands years of practice. The spindle consisted of a wooden shaft 20 to 30 centimeters long, with a haul, a disc of wood, stone, or clay mounted near the bottom that acted as a flywheel, storing rotational momentum. The spinner attached a starter thread to the spindle shaft, gave the spindle a spin to set it rotating, and fed wool fibers into the forming thread, the twist running up into the fibers and binding them together through friction. As the spindle descended, drawing out thread, The spinner's fingers controlled fiber feed rate and twist intensity, parameters that determined the thread's thickness and strength. This process sounds mechanical, but required extraordinary hand-eye coordination and tacit knowledge. Feed fibers too quickly and the thread becomes thick and weak. Too slowly and it becomes thin and breaks. Twist too much and the thread becomes stiff and kinked. Too little and it lacks strength. The optimal parameters varied with fiber type, intended thread thickness, and atmospheric humidity, requiring constant adjustment based on feel and visual assessment. Archaeological experiments attempting to replicate Viking spinning report that beginners produce thread of wildly inconsistent thickness that breaks frequently, while experienced spinners produce remarkably uniform thread almost automatically, their hands working from muscle memory while their attention focuses elsewhere. The quantity of spinning required for even simple textile projects staggers modern comprehension. A shirt might require 1,000 meters of thread for the warp and another 1,000 meters for the weft, the horizontal threads interwoven through the warp. Spinning 1,000 meters of thread takes an experienced spinner approximately 10 to 15 hours, meaning the thread for a single garment represented 20 to 30 hours of spinning. A family requiring 5 complete outfits needed roughly 50,000 meters of thread, representing perhaps 150 hours of spinning or 6 full days of continuous work. In practice, spinning was done in fragments an hour here while tending children, 30 minutes there while watching livestock accumulated over months until sufficient thread existed to begin weaving. Thread could be used single ply as spun directly from the spindle, but stronger, more durable thread came from plying, twisting 2 or more single-ply threads together in the opposite direction from their original spin. If single threads were spun clockwise, Z-twist, plying happened counterclockwise, S-twist, the opposing twists locking the component threads together and preventing them from unraveling. Plying roughly doubled production time, but created thread with triple the strength of single-ply thread of equivalent thickness, making it worthwhile for items receiving heavy use, like ship sails, cloaks, and work clothing. The warp-weighted loom, found in virtually every excavated Viking dwelling substantial enough to have a dedicated working area, represents a sophisticated engineering solution to the problem of maintaining consistent tension on hundreds of individual threads. The loom consisted of 2 vertical posts supporting a horizontal beam near their top, with a heddle rod, a horizontal bar suspended by cords hanging about halfway down. The warp threads hung from the upper beam, passed through the heddle rod, and continued down to the clay or stone weights at the bottom. These weights, typically 15 to 20 of them for a 1-meter wide fabric, each held multiple warp threads and kept them taut through gravity. Setting up the loom required careful planning and hours of preparation. The weaver first calculated thread requirements for a fabric 1 meter wide. With 10 threads per centimeter, she needed 1,000 warp threads, each perhaps 3 meters long, to weave a 2-meter piece with enough extra for attaching to the loom. These threads were measured, cut to length, and organized into groups that would hang from each weight. The upper ends were tied to the top beam, the lower ends attached to weights, and the heddle rod inserted between alternate threads, passing in front of odd-numbered threads and behind even-numbered ones. This setup, which might take an entire day for a complex weaving, allowed the weaver to create a shed, the space between raised and lowered warp threads, through which the weft thread passed. Weaving proceeded from top to bottom on the warp-weighted loom. The weaver pulled the heddle rod forward, raising half the warp threads and creating a triangular shed. She passed a weft thread through this shed, typically by hand, or using a smooth shuttle or netting needle that carried thread without snagging on warp threads. Then she pushed the heddle rod back, lowering the threads it held and raising those it didn't, creating the opposite shed. Another weft pass, this time going the opposite direction. After several weft passes, she used a weaving sword, a flat wooden blade with a pointed tip, to beat the weft threads upward, compacting them against the already woven fabric and creating dense, durable cloth. The rhythm of weaving pull heddle, pass weft, push heddle, pass weft, beat with sword, repeat could be maintained for hours once established, producing perhaps 10 to 15 centimeters of fabric per day for an experienced weaver working continuously. But few weavers worked continuously. Weaving happened in sessions between other responsibilities, meaning a 10-meter piece might take weeks or even months to complete. During this time, the fabric slowly grew downward from the top beam, the weights descending as warp threads were consumed until the woven portion grew too long to reach comfortably. At that point, the weaver would unroll the completed section, rolling it around the top beam to move the working area back within reach. The variety of weaves Vikings produced demonstrates sophisticated understanding of how thread interlacement patterns affect fabric properties. The simplest weave tabby or plain weave alternated weft, over-under through warp threads, creating fabric with equal strength in both directions. Twill weaves, where weft threads passed over 2 or more warp threads before going under one, created diagonal patterns and produced fabric with greater flexibility and drape than tabby weave. Diamond twill, where the direction of the diagonal pattern reversed regularly, created elaborate geometric patterns that appeared on high-status garments. Tablet weaving, a technique using square cards with holes in each corner. Threads passing through the holes created strong decorative braids used for trim, belts, and straps. Color transformed plain fabric into something precious. Natural sheep wool came in shades from white through grey and brown to nearly black, providing some color variation without dyeing. But vibrant colors, reds, blues, yellows, greens, required dyes extracted from plants, minerals, or in rare cases, animals. Madder root, cultivated in gardens or imported from warmer regions, produced reds ranging from brick orange to deep crimson depending on the dyeing process. Woad, grown across northern Europe, yielded blues when its leaves were fermented and their indigo content extracted. Weld, a common wild plant, gave yellows. Lichens scraped from rocks produced purples and browns. Walnut hulls created rich brown tones. The dyeing process required expertise as sophisticated as weaving itself. Dyestuffs rarely attached directly to wool fibers. They needed a mordant, a chemical compound that bonded with both fiber and dye, creating a stable connection. Alum, imported at considerable expense from Mediterranean regions, was the primary mordant, though iron sulfate from bog deposits could substitute for darker colors. The dyer dissolved mordant in water, heated it to near boiling, added wool, and maintained temperature for an hour or more, allowing the mordant to penetrate fibers. Then she removed the wool, added dyestuff to the same bath, returned the wool, and maintained heat for another hour while color developed. The complexity came from controlling variables, temperature, time, pH, and the ratios of mordant, dye, and fiber, all without thermometers, timers, or measuring instruments beyond experience and judgment. Color fastness, the dye's resistance to fading from light, washing, or abrasion, varied enormously. Madder, properly applied, produced colors that could last decades. Inferior dyeing techniques or cheaper substitutes might fade within months of exposure to sunlight. This meant color signaled not just aesthetic preference but quality and expense. A deep red cloak represented dozens of hours of skilled work, and imported materials worth substantial sums. Saga accounts mention clothing colors by name, suggesting that people noticed and valued these distinctions, though the specific shades they meant by scarlet or blue-black remain uncertain since color terminology changes over time. Finishing processes, after weaving and dyeing, transformed fabric from loose cloth into proper material for garments. Fulling soaking wool fabric in water and pounding it repeatedly caused fibers to felt slightly, shrinking the fabric and creating a denser, more water-resistant material. The process used stale urine again, its ammonia content helping fibers bond. After fulling, fabric was stretched on tenter frames, wooden frames with hooks around the edges to dry while being pulled back to desired dimensions, preventing excessive shrinkage. The dried fabric was then brushed with teasels, dried flower heads covered with tiny hooks that raised a nap on the surface, making the fabric softer and trapping air for better insulation. Sailcloth represented textile production's ultimate challenge. A typical Viking ship's sail measured approximately 11 meters by 11 meters, 121 square meters of extremely robust fabric that had to withstand tremendous wind loads while remaining flexible enough to handle and light enough that the mast could support it. Archaeological analysis of sail fragments found in Viking contexts shows they were woven from coarse wool, probably from tog fibers, in a dense tabby weave with perhaps 5 threads per centimeter in both warp and weft. This meant a single sail required approximately 60,000 meters of thread, 600 hours of spinning before weaving could begin. The weaving itself, given the required fabric area and thread density, might take a team of weavers 3 to 6 months of dedicated work. The sail was almost certainly woven in strips 30 to 40 centimeters wide, and the maximum practical width on a warp-weighted loom, then sewn together edge to edge with linen thread to create the full dimensions. This sectional construction had advantages beyond overcoming loom width limitations. Damaged sections could be replaced without discarding the entire sail, and the seams created reinforced lines that helped distribute stress. The finished sail was then coated with animal fat, linseed oil, or pine tar to increase water resistance, transforming the wool from absorbent to relatively waterproof. This treatment added significant weight. A sail coating might weigh 20 to 30 kilograms but prevented the sail from absorbing its own weight in water during rain or spray. The labor investment in a sail exceeded that of constructing the ship itself. Where a ship required perhaps 8,000 hours of skilled carpentry, a sail represented over 1,000 hours of spinning, weaving, and finishing, and that's assuming a team of women worked simultaneously on different sections. This massive labor input had to be repeated every few years, as sails wore out from ultraviolet degradation, salt exposure, and mechanical stress. No wonder early medieval ship descriptions specify sails among the vessel's most valuable components, and saga accounts mention sails as notable gifts between rulers. But beyond the documented techniques and hours of labor, deeper questions remain about the knowledge systems that made this production possible. How did spinners develop the hand coordination to produce uniform thread? Modern textile artists attempting to replicate Viking spinning report that it takes months of daily practice to approach the consistency evident in archaeological thread samples. What training methods transmitted these skills? Did young girls begin with coarse thread, gradually developing the sensitivity to produce finer work? Or did they watch experienced spinners for years, internalizing the visual patterns of proper technique before attempting it themselves? Similarly, how did weavers learn the complex patterns of twill weaves? Written descriptions of how to create herringbone or diamond patterns are confusing even with diagrams, yet Viking weavers produced these patterns flawlessly, sometimes combining multiple pattern types in a single fabric, suggesting they possessed mental models of thread interlacement that guided their hands without conscious calculation. Did they use physical aids, sample cards showing the pattern sequence, or was everything memorized? Did master weavers develop new patterns through experimentation, or were patterns traditional, passed down unchanged across generations? The economics of textile production shaped Viking Age society in ways modern people struggle to appreciate. When clothing required hundreds of hours to produce, fashion changed slowly. Garments were worn, repaired repeatedly, passed down through families, and finally recycled into cleaning rags or burial shrouds. The concept of disposable clothing didn't exist. A woman's weaving skill determined her family's comfort and her own social standing. A skilled weaver could produce enough fabric to clothe her family and create surplus for trade. Poor quality weaving meant inadequate clothing, cold winters, and lower social status. This created interesting power dynamics. While men controlled fields, livestock, and warfare, women controlled textile production, a domain that included not just clothing but sails, tents, wall hangings, and bedding. A wealthy woman might supervise several servants or slaves spinning and weaving under her direction, functioning as a textile production manager. The keys she wore symbolizing control over locked storage chests containing wool, dyed thread, and finished cloth represented real economic power. In funeral archaeology, oval brooches, the distinctive paired brooches Viking women wore, are often found with textile working tools, including spindle whorls, needles, and small shears, suggesting that even in death, women's identity connected closely with textile production. The end of traditional Viking textile production came not through sudden abandonment but gradual obsolescence. As trade expanded in the 12th and 13th centuries, imported fabrics from Flanders and England became available, produced in early textile factories using horizontal looms with foot-powered treadles that wove faster than warp-weighted looms, creating standardized cloth more cheaply than household production. By the 1400s, most Scandinavians purchased rather than produced their clothing, and the complex skills of spinning even thread, dyeing vibrant colors, and weaving intricate patterns survived mainly in remote rural areas where market access was limited. The last traditional warp-weighted looms operated in Iceland into the early 20th century, their persistence enabled by Iceland's isolation and limited cash economy that made household production economically competitive with imported goods. Photographs from the 1890s show Icelandic women working at looms almost identical to those found in Viking archaeological sites, demonstrating the technology's millennium-long persistence. But even in Iceland, industrialization eventually arrived. The last generation of women who learned weaving as a necessary life skill, not as a hobby or historical recreation, died mid-century, taking with them embodied knowledge that cannot be fully recovered from written sources or archaeological remains. Modern experimental archaeologists attempting to recreate Viking textiles face challenges that reveal gaps in our understanding. The basic techniques are documented, we know how spindles and looms work, but the details that distinguish adequate from excellent results remain unclear. How tight should thread twist be? How hard should weft threads be beaten? How much tension should warp threads carry? Written sources don't address these questions because they were too fundamental to require explanation, like modern instructions that say, "Cook until done," without specifying exact temperatures or times because experienced cooks know from observation and experience. The textiles themselves, preserved in a few waterlogged archaeological sites or as tiny fragments attached to metal artifacts, show what was achieved but not how. Thread counts can be measured, twist directions observed, dye chemistry analyzed through spectroscopy. But the weaver's decision-making process, why this pattern, rather than another, how she judged when thread quality was acceptable, what she considered excellence versus adequacy, remains hidden. The artifacts answer what, but not why or how. Standing in a museum examining a fragment of Viking-age wool fabric, preserved by chance in a ship burial's waterlogged conditions, you can see the thread count, the weave pattern. The remnant color faded to brown by centuries underground. You can read the label explaining it's from the 10th century, woven on a warp-weighted loom dyed with madder. But you cannot feel the weight the weaver felt as clay loom weights pulled warp threads. Taut. You cannot hear the rhythmic scrape of the weaving sword packing weft threads. You cannot smell the lanolin in wool not yet cleaned completely, or the ammonia of fulling baths, or the earthy scent of plant dyes simmering in iron cauldrons. The fabric survived. The labor that created it is documented through experimental archaeology, but the experience of creating, the satisfaction of producing cloth from wool, the frustration when thread broke, the pride in a complex pattern executed flawlessly that died with the last women who wove not for historical recreation, but because their families needed clothing and they had the knowledge to produce it. What remains are questions we're learning to ask but cannot fully answer. How did it feel to possess skills so fundamental to survival that their absence meant cold, poverty, and social exclusion? How did it feel to spend thousands of hours producing something as basic as cloth, yet to know that without your work, your family would freeze? The threads that clothed Vikings, that caught wind in their sails, that decorated their halls, they're preserved fragmentarily in museums and archaeological reports. But the knowledge that created those threads, the hands that worked for hours daily across decades, the eyes that judged quality through experience that remains accessible only partially, through experimental archaeology that recreates techniques while acknowledging we cannot recreate the context that made those techniques not museum demonstrations, but essential survival skills. On a farm in northern Norway, as September's light begins its retreat toward winter darkness, a family works frantically to preserve the season's harvest before temperatures drop and snow buries everything under meters of white. They have perhaps 6 weeks to transform summer's abundance into forms that will survive until next spring: salting fish, drying meat, fermenting vegetables, smoking cheese, and storing grain. Failure means starvation. There are no grocery stores, no supply chains, no emergency services. The food they preserve now, through techniques refined over centuries, must sustain them through 5 months when nothing grows and the sun barely rises above the horizon. This is not agriculture, as modern people understand it, seasonal activity that supplements year-round food access, but an existential challenge where survival depends on transforming perishable abundance into imperishable reserves. The fundamental problem facing Norse farmers was entropy. Meat rots within days at room temperature as bacteria consume it. Vegetables decay. Grain becomes moldy. Dairy products spoil. Every harvest represents temporary abundance that nature immediately begins reclaiming. Preservation techniques work by creating conditions hostile to the microorganisms that cause decay: too salty, too dry, too acidic, too cold, or too smoky for bacteria and fungi to thrive. Vikings didn't understand microbiology. They knew only that certain processes worked, knowledge accumulated through generations of trial and error, where failure meant death and success meant survival to reproduce and teach the next generation. Fish preservation dominated coastal economies because fish, while abundant during certain seasons, spoils rapidly. Within hours of death, fish begins decomposing as internal enzymes break down tissue and bacteria proliferate. Norse fishermen developed multiple preservation methods, each suited to different fish species and intended storage durations. The simplest method, drying, exploited Scandinavia's cold, dry winter winds. Cod, the primary species for this treatment, were cleaned immediately after catching, their heads removed and entrails discarded, then hung on wooden racks called hyel in pairs, tied through the tail. The Arctic wind and low humidity created conditions where moisture evaporated faster than bacteria could multiply, desiccating the fish into boards hard as wood that could last years without spoiling. This stockfish, as dried cod became known, transformed into a commodity that sustained exploration and trade. A Viking ship departing for Iceland or Greenland might carry a ton of stockfish, lightweight, compact, and requiring no refrigeration, providing reliable protein for voyages lasting weeks. The fish required rehydration before eating, achieved by soaking in water for several days, which restored edibility, though never quite returning the fish to fresh texture. Archaeological analysis of medieval trade goods shows stockfish reached Mediterranean markets, travelling thousands of kilometres from Norway to Italy. its preservation allowing commerce across distances that would be impossible with fresh fish. Salting provided another preservation method, particularly for oily fish like herring that didn't dry well due to high fat content. Salt draws moisture from fish through osmosis, while creating a hostile environment for bacteria. The process began with layering cleaned fish with coarse salt in barrels or clay vessels, alternating fish and salt in ratios determined by experience. Too little salt, and the fish would spoil; too much, and it became inedible. After several days, the fish released their moisture, creating brine that was periodically drained and replaced with fresh salt. The resulting saltfish could last months, though it required soaking before cooking to remove excess salt. But salt itself represented a problem. Scandinavia's cold climate made solar evaporation of seawater impractical for large-scale salt production. Most salt was imported from the Baltic coast or, more expensively, from Mediterranean regions, making it a valuable commodity. The economics of preservation required balancing salt costs against the value of preserved food. Wealthy households could afford to heavily salt premium fish, while poor families used minimal salt and relied more on drying or smoking. This created a preservation hierarchy where the same fish species received different treatments depending on the producer's economic status. Smoking combined drying with the antimicrobial properties of wood smoke compounds. Fish or meat was hung in specialized smokehouses, small buildings with fire pits at ground level, and racks several meters above where food hung in rising smoke. The process took days to weeks depending on desired preservation level. Hot smoking at temperatures around 70 degrees Celsius cooked the food while drying and impregnating it with smoke, creating products meant for consumption within weeks. Cold smoking at temperatures below 30 degrees Celsius preserved without cooking, creating harder, longer-lasting products. The choice of wood mattered. Different species produced smoke with varying flavors and preservative qualities. Juniper was prized for its strong antimicrobial compounds and distinctive flavor, while birch provided milder smoke suitable for delicate fish. Meat preservation followed similar principles but with different challenges. Large animals, cattle, horses, sheep, pigs, were typically slaughtered in late autumn after fattening on summer pasture, but before winter feeding became necessary. This created a sudden abundance of meat that had to be preserved immediately. Some meat was salted using the same techniques as fish, packed in barrels with alternating layers of salt, hanging meat in the longhouse rafters, where rising smoke from the central hearth continuously bathed it in smoke while the building's cold air temperatures slowed bacterial growth, preserved meat for months. This ambient smoking didn't produce the heavily smoked flavor of dedicated smokehouses, but provided adequate preservation while utilizing existing conditions. Sausage making allowed use of meat scraps and organ meats that wouldn't preserve well otherwise. Ground meat was mixed with salt, spices if available, and sometimes blood, then stuffed into cleaned intestines that acted as periphi, casings. These sausages were then smoked or dried, the casing allowing moisture to escape while preventing direct contact with air that would cause rapid spoilage. The fermentation that occurred during sausage production before smoking or drying killed the bacteria involved, created acidic conditions that contributed to preservation, and developed complex flavors. Modern analysis of traditional Scandinavian sausages shows they contain lactobacillus bacteria, similar to those in yogurt and cheese, suggesting controlled fermentation was understood even if the microbiology wasn't. Dairy preservation presented unique challenges because milk spoils within hours at room temperature. The solution was transformation into products where preservation was intrinsic to production. Cheesemaking converts liquid milk into solid form, where reduced moisture content and, in some styles, high salt content inhibit bacterial growth. The basic process adding rennet to warm milk to coagulate proteins, cutting the resulting curds, draining whey, and pressing curds into a solid mass creates fresh cheese that lasts days. For longer storage, the cheese was aged in cool, dry conditions where surface molds created protective rinds, while interior moisture continued reducing through evaporation. Skyr, the Icelandic cultured dairy product, represents another preservation strategy. Made by warming milk, adding bacterial cultures from previous batches, and allowing fermentation for 12 to 24 hours, Skyr achieves a pH low enough that harmful bacteria cannot survive. The resulting thick, yogurt-like product could be stored for weeks, providing protein and calories when fresh milk was unavailable. The bacterial cultures required to make Skyr had to be maintained continuously. Each batch used culture from the previous batch, creating an unbroken chain stretching back generations. Families guarded their Skyr cultures carefully. Losing the culture meant losing the ability to produce Skyr until obtaining starter from neighbors or relatives. Butter preservation required different techniques, because butter's high fat content makes it prone to rancidity rather than bacterial spoilage. One method involved packing butter tightly into containers, wooden barrels, clay vessels, or even hollowed-out animal stomachs, then burying them in peat bogs. The peat's acidity and low oxygen content prevented oxidation that causes rancidity, preserving butter for months or even years. Bog butter finds are common in Ireland and occasionally in Scandinavia, suggesting this practice was widespread. Whether the butter was always intended for retrieval or sometimes represented offerings to gods or spirits remains debated, as some finds show no signs of attempts at recovery. Grain storage seems simpler than preserving animal products. Grain naturally dries to low moisture content and stores well in dry conditions. But achieving those conditions in Scandinavia's damp climate required careful management. Grain had to be harvested at optimal ripeness too early, and high moisture content promoted mold too late, and grain shattered from stalks during harvesting. After cutting, grain was bundled and shocked in fields for several days, allowing further drying before transport to storage. Some farms had dedicated grain-drying buildings with adjustable shutters and raised floors allowing air circulation, where grain could be spread in thin layers and dried thoroughly before bagging or storing in sealed containers. The enemies of stored grain were numerous. Mice and rats consumed vast quantities if allowed access. Insects infested grain, their larvae boring through kernels and rendering them inedible. Mold grew in damp conditions, producing toxins that could sicken or kill humans who consumed the grain. Protection required multiple strategies: storage containers elevated off damp ground, regular inspection, and removal of infested grain. Sometimes the addition of aromatic herbs whose compounds repelled insects. Archaeological evidence from Viking-age grain storage pits shows they were lined with birch bark, which contains compounds toxic to many insects, and were sealed with clay to limit air and moisture penetration. Vegetables presented perhaps the greatest preservation challenge because most contain high water content and have tender cell walls that break down quickly. Root vegetables, carrots, turnips, onions could be stored in cool, dark conditions for months if kept dry and prevented from sprouting. Some farms had dedicated root cellars dug into earth where temperature remained stable year-round, typically 4 to 7 degrees Celsius, too cold for rapid spoilage but above freezing. These cellars had to be carefully ventilated to prevent carbon dioxide accumulation from vegetable respiration, which could create conditions dangerous to humans entering the space. Cabbage preservation through fermentation produced sauerkraut, a staple that provided vitamin C during winter when fresh vegetables were unavailable. The process required only shredded cabbage and salt, layered in vessels and compressed to express juice. Natural bacteria on the cabbage converted sugars to lactic acid, creating acidic conditions that preserved the cabbage while developing distinctive flavor. The fermentation took several weeks, during which the vessel had to be monitored to ensure the cabbage remained submerged in brine. Exposed cabbage would mold. The resulting sauerkraut could last months and provided essential nutrients that prevented scurvy during long winters. But fermentation was unpredictable. With medieval technology, sometimes it proceeded properly, creating safe, preserved food. Other times, contaminating organisms produced toxins or off flavors that rendered the batch inedible. The difference between successful and failed fermentation often came down to factors invisible to medieval producers: the specific bacterial species present, temperature during fermentation, exact salt concentration, knowledge of what constituted proper fermentation conditions, accumulated through experience, transmitted as rules like keep the cabbage submerged or ferment in cool weather, not warm, guidelines based on observation rather than understanding of underlying microbiology. Honey, rare and valuable, was one of few foods that required no preservation. Its low water content and acidic pH naturally prevented bacterial growth. A sealed container of honey could last indefinitely. Beekeeping was practiced to varying degrees, with some farms maintaining hives and harvesting honey annually, while others relied on wild honey collected from hollow trees where bees established colonies. Honey served not just as sweetener but as medicine applied to wounds. Its antimicrobial properties prevented infection and as fermenting agent for mead, the honey wine that features prominently in Norse literature and social customs. The preservation calendar dictated the farming year's rhythm. Spring through summer focused on production planting, tending, and harvesting. Autumn became preservation season, a frantic period when everything had to be processed before winter. Winter was consumption season, carefully rationing preserved foods to last until spring. This created an annual cycle of feast and potential famine, with late winter and early spring being the hungry season when previous year's stores dwindled and new growth had not yet begun. Successful preservation meant survival. Failed preservation meant starvation. The social organization of preservation created interesting dynamics. Large farms with multiple workers could specialize, some people fishing while others salted, some butchering while others smoked meat, creating efficiency through division of labor. Small farms with few hands required everyone to know all techniques, though perhaps mastering none completely. Women typically managed dairy preservation and some vegetable fermentation, while men handled fish smoking and meat curing. Children learned by assisting, gradually taking on more responsibility as they matured. By adulthood, everyone possessed comprehensive knowledge of preservation techniques, a knowledge literally critical to survival. Yet despite this universal knowledge, preservation failures occurred. Sagas mention famine years when preserved food spoiled or ran out before spring, forcing families to slaughter breeding stock or seek aid from neighbors. The Icelandic Gragas law code includes provisions for famine relief, indicating that periodic food shortages were expected, and communities developed formal systems for resource sharing during crises. This suggests preservation was never perfectly reliable. Even experienced practitioners occasionally lost entire batches to spoilage, and unusual weather could create conditions where standard techniques failed. The transition away from traditional preservation began gradually as trade networks expanded. By the 1200s, imported grain could buffer local harvest failures. Salt became more available and affordable as Baltic salt trade expanded. Eventually, glass jars with sealed lids allowed new preservation methods unknown to Vikings. But the fundamental shift came with industrialization, canning in the 1800s, mechanical refrigeration in the 1900s, and finally, the global supply chains that allow modern Scandinavians to eat fresh tropical fruit in midwinter, something that would have seemed like magic to their ancestors. The last generation to depend primarily on traditional preservation methods probably lived in the late 1800s, in remote rural areas where market access remained limited. Photographs from that era show smokehouses, drying racks, and root cellars still in use, though increasingly supplemented by purchased goods. By the mid-1900s, even remote farms had access to modern preservation methods, and the old techniques survived, primarily as traditions, making dried fish for cultural reasons rather than necessity. fermenting cabbage because families enjoyed the taste rather than needed the preserved food. What's been lost isn't just techniques we can document how stockfish was made, but the embodied knowledge of when techniques would work. How did a smoker know when fish had dried sufficiently? How did a butter maker judge when butter was ready for bog storage? How did families decide which preservation method to use for which items, balancing labor costs against storage duration and food quality? These decisions involved multiple variables assessed simultaneously through experience, creating intuitive judgments that functioned reliably but resist codification into explicit rules. Modern experimental archaeologists attempting Viking preservation methods report mixed results. Making stockfish works reliably when weather cooperates, but unexpected rain or warmth can ruin entire batches. Fermentation sometimes produces excellent results, other times creates inedible messes. These inconsistencies suggest that Viking Age practitioners possessed sophisticated understanding of conditions required for success. Understanding developed through years of observation, but never formalized into written instructions. They knew what modern researchers are relearning, that preservation is as much art as science, requiring judgment and adaptation to specific conditions rather than rigid adherence to recipes. The archaeology of preservation is challenging because preserved food was meant to be consumed. Successful preservation leaves no trace. What survives are the facilities and tools: smokehouses, salt-encrusted barrels, ceramic storage vessels, wooden drying racks preserved in waterlogged conditions. These artifacts tell us that preservation happened, but provide limited information about specific techniques. Written sources mention preserved foods saga. Characters eat stockfish, drink sour milk, consume salted meat, but rarely describe how these items were produced. The knowledge was assumed, too basic to require explanation, yet too complex to be obvious from artifacts alone. Standing in a reconstructed Viking farmhouse, seeing the smokehouse out back and the root cellar underground, you can imagine the autumn work, the urgent processing of fish and meat and vegetables before winter makes it impossible. But you cannot feel the anxiety of a family whose preservation attempts are failing, watching food spoil that represents the difference between survival and starvation. You cannot experience the relief when sealed barrels of saltfish are stored away, knowing winter's hunger is forestalled. You cannot taste the late winter meal of stockfish and fermented cabbage, monotonous but life-sustaining, that represents successful preservation techniques applied months earlier. The food survived only long enough to sustain one winter, then was consumed. The preservation techniques survived longer, passed through generations until they became unnecessary. What remains now are reconstructions based on incomplete information, experiments that sometimes succeed and sometimes fail, and questions about the experiential knowledge that distinguished Vikings who survived winter after winter from those whose preservation failures led to hunger or death. We know they preserved food successfully for centuries. We know roughly how they did it, but we don't fully understand what they knew, the accumulated wisdom of generations who faced winter's siege and survived through transformation of abundance into reserves that outlasted the darkness. In a laboratory at the University of Copenhagen, a geneticist examines DNA sequences extracted from bones buried in a 10th century grave in northern England. The sequences reveal something unexpected. This individual, interred with Norse weapons and buried according to Scandinavian customs, carries genetic markers linking them to populations from the British Isles, not Scandinavia. The findings suggest something more complex than simple invasion and replacement. Instead, a process of cultural adoption, intermarriage, and identity transformation that makes defining Viking more complicated than simple genetic ancestry. This ambiguity echoes through everything the Vikings left behind: settlements whose inhabitants mixed Norse and native populations, languages that borrowed words in both directions, legal systems that blended Scandinavian and local traditions, and technologies that merged innovations from multiple cultures. What survived the Viking Age wasn't pure Norse culture transplanted intact, but hybrid forms created through contact, conflict, and cooperation. The genetic legacy appears throughout the North Atlantic world. In Iceland, genetic analysis shows the population descends from Scandinavian men and women from both Scandinavia and the British Isles. Roughly 60% of male lineages trace to Scandinavia, while 60% of female lineages trace to the British Isles and Ireland. This asymmetry suggests Viking Age settlement involved Norse men taking wives from populations they encountered, whether through voluntary marriage, capture, or economic necessity. Similar patterns appear in Orkney, Shetland, and the Hebrides, where modern populations show substantial Scandinavian genetic contribution mixed with indigenous ancestry. But genetics tells only part of the story. Cultural identity proved more fluid than biological descent. In Normandy, Scandinavian settlers arrived beginning in the late 9th century, established the Duchy of Normandy by 911 CE, and within 2 generations had adopted French language and customs so thoroughly that little obvious Norse culture remained. By the time Duke William conquered England in 1066, the Normans were culturally French, despite their Scandinavian origins barely 150 years earlier. This rapid assimilation suggests that Viking identity was more about behavior and culture than ancestry. When circumstances favored adoption of local culture, Scandinavian populations did so readily. Language provides the most visible everyday legacy. English contains approximately 2,000 words of Old Norse origin, borrowed during the Viking Age when Scandinavian settlers controlled much of northern and eastern England in the region known as the Danelaw. These aren't obscure technical terms but fundamental vocabulary. Sky, window, knife, anger, trust, law, and the pronoun they all come from Old Norse. The grammatical simplification of English loss of many inflected forms that made Old English as complex as Latin may also result from contact between speakers of Old English and Old Norse, 2 related but distinct languages. When adults learning a second language as immigrants simplified grammar while speaking, and their bilingual children grew up hearing both simplified immigrant speech and native forms, the simplified versions sometimes won out because they worked adequately for communication while requiring less memorization. Place names preserve the Viking presence in more permanent form. Across northern England and eastern Scotland, towns ending in by, farmstead, thorp, outlying settlement, toft, homestead, or thwaite, clearing mark, areas of Scandinavian settlement. Grimsby, Scunthorpe, Lowestoft, Braithwaite, hundreds of such names survive, creating a linguistic map of Viking Age colonization visible on modern road signs. In Iceland, virtually all place names are Old Norse in origin, though the language itself evolved differently in isolation than it did in Scandinavia, creating modern Icelandic, a language much closer to Old Norse than modern Norwegian, Swedish, or Danish. Legal systems show surprising Norse influence. The word law itself comes from Old Norse lagu, and many fundamental legal concepts entered English through Scandinavian contact. The jury system, where groups of community members determine facts of a case, has potential roots in Norse practices of communal decision-making at thing assemblies. Iceland's Alþingi, established in 930 CE, claims to be the world's oldest parliament, though this involves generous interpretation of parliament and ignores discontinuities in its existence. Nevertheless, the concept of representative assemblies making collective decisions appears strongly in Norse tradition and may have influenced development of similar institutions elsewhere. The Viking Age's material legacy is surprisingly limited. Few buildings survive from the period. Longhouses were wooden structures that rotted away within decades unless preserved by unusual conditions. Most metal artifacts were recycled. Iron was too valuable to bury permanently, and even high-status graves often contain weapons and tools showing signs of previous use and repair. What survives are items accidentally lost or deliberately buried as hoards and never recovered. The Quairdale hoard, discovered in England in 1840, contained over 8,000 silver coins and metal fragments weighing 40 kilograms, an enormous sum buried around 900 CE and never retrieved, though whether as safekeeping during danger, religious offering, or some other purpose remains unknown. These hoards provide evidence of Viking-age trade networks spanning from Baghdad to Newfoundland. Silver dirhams minted in Islamic territories appear in Scandinavian hoards alongside Byzantine coins, Anglo-Saxon pennies and Frankish denarii. The sheer diversity of coin origins suggests either extensive trade networks or significant raiding activity that brought exotic items back to Scandinavia. Analysis of silver composition using spectroscopy allows tracing specific artifacts to their production regions, revealing that metal moved through multiple hands across thousands of kilometers, melted and recast repeatedly while retaining chemical signatures of its origins. Ship technology represents perhaps the Vikings' most consequential legacy. The clinker-built hull overlapping planks fastened with rivets continued in northern European shipbuilding through the medieval period, and influenced vessel design even after newer construction methods appeared. The side-mounted rudder persisted until the 13th century, when stern-mounted rudders proved more effective for larger ships. More subtly, the Viking demonstration that ocean crossing was feasible with relatively small vessels encouraged subsequent European maritime exploration. When Columbus crossed the Atlantic in 1492, he did so in ships not dramatically larger than Viking vessels. Following routes that passed relatively close to the path, Leif Erikson had travelled 5 centuries earlier, but the Viking voyages to North America left almost no lasting impact on the continent itself. The settlement at Lansort Meadows in Newfoundland operated for perhaps a decade around 1000 CE, then was abandoned. A few iron nails, some wood chips from shipbuilding, and post holes from 3 buildings comprise the physical evidence. No genetic legacy appears in indigenous North American populations. DNA analysis shows no Scandinavian contribution detectable above background noise. No Old Norse words entered indigenous languages. The encounter between Vikings and native peoples, documented in saga accounts of both trade and conflict, left no lasting cultural exchange because the settlement failed. Unlike Iceland or Greenland, where no indigenous populations existed to resist colonization, North America contained established societies that limited Norse expansion to a brief, failed toehold. Greenland's Norse settlement lasted longer, but ultimately met the same fate. Established around 985 CE, the settlements persisted for roughly 450 years, before disappearing sometime in the mid-1400s. The reasons remain debated. Climate cooling during the Little Ice Age, making farming increasingly marginal. Loss of contact with Iceland as Atlantic voyaging decreased. Conflict with Inuit populations expanding southward. Economic decline as European demand for Greenlandic goods diminished, or some combination of all these factors. Archaeological evidence shows the later inhabitants struggled. Isotope analysis of bones indicates diet shifted increasingly toward marine resources, suggesting terrestrial farming had become inadequate. The last documented contact with the settlement was in 1410, when an Icelandic ship stopped at Greenland. After that, silence. When Europeans next visited Greenland in the early 1500s, they found ruins but no Norse population. This failure of Greenland's settlement, the most remote successful Norse colony, suggests limits to Viking Age expansion. With medieval technology, some regions could be colonized successfully while others exceeded sustainable limits. Iceland succeeded because its climate, while harsh, allowed sufficient farming and fishing to support a population. Greenland succeeded marginally, its settlements always precarious and dependent on trade with Iceland and Norway. North America exceeded these limits too distant from supply sources, containing populations resistant to displacement offering insufficient economic incentives to justify the enormous effort required to maintain contact across the North Atlantic. The transformation of Viking culture itself represents another kind of legacy. The conversion to Christianity, beginning around 900 CE and largely complete by 1100 CE, fundamentally altered Norse society. The old gods, Odin, Thor, Freya, became literary figures rather than objects of worship. The Thing assemblies that combined political and religious functions became secular courts. The runestones that had recorded both mundane transactions and mythological allusions began carrying Christian prayers and symbols. Within a few generations, the pagan Viking Age had become a Christian medieval period, with the earlier era surviving in memory and literature rather than living practice. This cultural discontinuity complicates claims of continuous tradition. When modern groups claim to practice Viking traditions, they're inevitably engaging in reconstruction rather than continuation, because the chain of transmission was broken centuries ago. We can analyze artifacts, translate texts, and conduct experimental archaeology, but we cannot recover the lived experience of Viking Age people or the unwritten knowledge that died when the last practitioners passed away. What we call Viking culture is partially our construction, built from fragmentary evidence and necessarily incomplete understanding. Yet some aspects of Norse culture did persist through transformation rather than disappearing entirely. The Icelandic sagas, though written in the 13th and 14th centuries, 200 to 400 years after the events they describe, preserve oral traditions from the Viking Age. These texts, written in Old Norse, contain detailed accounts of exploration, settlement, legal disputes, and daily life that provide information available nowhere else. Modern Icelanders can read these sagas in the original language with little difficulty, creating an unusual continuity between medieval and modern literature. This linguistic conservatism, Iceland's isolation, allowed its language to evolve more slowly than mainland Scandinavian languages, creates the illusion of closer connection to the Viking Age than actually exists. The language is similar, but the culture is fundamentally different. The romanticization of Vikings in popular culture, beginning in the 19th century, created perhaps the most visible legacy, one largely divorced from historical reality. Horned helmets, which Vikings never wore in battle, became standard iconography. The Vikings were reimagined as either noble savages, uncorrupted by civilization, or as proto-fascist warriors embodying racial purity and martial virtue. Neither image reflects the complex, multicultural reality of the Viking Age, where Scandinavian raiders and traders encountered, fought, married, and exchanged ideas with peoples from Africa to Asia. These imagined Vikings serve modern purposes, national identity, construction, political ideology, entertainment, rather than representing historical truth. This raises uncomfortable questions about whose purposes the Viking legacy serves. Nationalist movements in Scandinavia sometimes invoke Viking heritage to claim cultural superiority or racial homogeneity, ignoring the Viking Age's extensive cultural mixing and the modern population's complex ancestry. White supremacist groups occasionally appropriate Norse symbols while demonstrating no understanding of Norse history or culture. Meanwhile, serious scholarship continues, revealing the Viking Age's complexity, finding evidence of diversity, trade, cultural exchange, and adaptability that contradicts simplistic narratives of isolated raiders spreading terror. The archaeological legacy continues growing, as new discoveries provide evidence that forces revision of established narratives. Recent excavations in Iceland have revealed settlements earlier than previously documented, pushing back colonization dates and suggesting multiple waves of settlement. DNA analysis of human remains continues revealing surprising ancestries and migration patterns. Chemical analysis of artifacts traces trade routes and production techniques. Each discovery adds detail while raising new questions, suggesting that our understanding of the Viking Age remains incomplete and subject to revision as evidence accumulates. But some questions may never be answerable. Did Viking Age people think of themselves as Vikings, or was that identity constructed retrospectively? The Old Norse word vikinga referred to raiding activity rather than ethnic identity. One went, I Viking, raiding. But being a Viking wasn't a full-time identity like being Norwegian or Icelandic. Yet modern usage treats Viking as an ethnic descriptor, suggesting a unified culture that probably never existed. The people we call Vikings likely thought of themselves primarily as Norwegians, Danes, Swedes, or Icelanders, with raiding being an occasional activity rather than defining characteristic. How much continuity exists between Viking Age Scandinavians and modern populations? Genetically, substantial most Norwegians, Swedes, Danes, and Icelanders descend primarily from Iron Age populations that became the Vikings. Culturally, very little Christianity, industrialization, democracy, and centuries of other changes have created societies that would be unrecognizable to their ancestors. The continuity is primarily geographic. Populations descended from Vikings still live in Scandinavia, but geographic continuity doesn't imply cultural continuity. Modern Scandinavians have no more special access to Viking culture than any other modern people studying historical evidence. What, then, is the Viking legacy? Genetically, a contribution to populations across the North Atlantic. Linguistically, thousands of borrowed words and place names. Technologically, advances in shipbuilding and maritime navigation. Culturally, saga literature and archaeological sites. But perhaps most significantly, the Viking Age demonstrates humanity's capacity for rapid cultural change. Within 3 centuries, Scandinavian populations went from pagan raiders to Christian kingdoms, from isolated agricultural communities to participants in pan-European political networks, from oral culture to literary production. This rapidity of transformation suggests that culture is more plastic than we often assume, capable of dramatic shifts within a few generations when circumstances favor change. The archaeological sites scattered across the North Atlantic burial mounds in Norway, ruined farmsteads in Iceland, abandoned settlements in Greenland, the single confirmed site in Newfoundland are monuments to both achievement and limitation. They mark the furthest extent of medieval European expansion, the limits of what could be accomplished with Viking Age technology and social organization. They also mark failure. Most of these sites are ruins, abandoned when the settlements they served could no longer sustain themselves. Success and failure intertwine inextricably in the Viking legacy, reminding us that even successful colonization is temporary when measured against geological timescales. Standing at Lansore Meadows, looking across the strait toward Labrador where Norse explorers encountered indigenous peoples 1,000 years ago, you can see what they saw: the same coastline, the same northern forest, the same cold waters. But you cannot see what they thought about this encounter, whether they felt wonder at discovering a new world or frustration at being unable to colonize it, whether they understood the indigenous peoples as human equals or as obstacles to overcome. The site answers where and when, but not why or how they thought. This gap between physical evidence and experiential understanding defines the Viking legacy. We have ships, but not the confidence of sailors who crossed oceans guided by stars and waves. We have weapons, but not the psychology of warriors who fought without modern medicine or certainty of survival. We have ruins of farms, but not the intimate knowledge of land possessed by families who worked the same fields for generations. We have the artifacts of Viking Age life, but not the life itself, the thoughts, feelings, hopes, and fears of people whose bones have been dust for centuries. What we call the Viking legacy is really our reconstruction of their legacy, built from evidence they left behind, but shaped by our concerns and questions. Each generation asks different questions of the Viking Age. The 19th century sought national origins. The 20th century asked about migration and colonization. The 21st century explores genetic diversity and climate adaptation. The Vikings themselves had no concept of legacy, no awareness that archaeologists would excavate their settlements or that their DNA would be analyzed. They lived, worked, fought, loved, and died, leaving behind material evidence that we interpret through lenses they couldn't have imagined. Perhaps that's the deepest legacy, not what they intended to leave, but what accidentally survived. A ship preserved in a burial mound, coins dropped and lost in fields, DNA and bones buried in forgotten graves. These unintentional time capsules carry information the Vikings themselves didn't know they were transmitting. Trade networks revealed through coin hoards they meant to recover, dietary information preserved in bones they expected would decay, construction techniques visible in buildings they thought would stand forever, but which collapsed centuries ago. The Viking Age ended not through catastrophic collapse, but gradual transformation as Scandinavia integrated into Christian European culture. The last traditional Viking raid occurred in the early 1100s, though the date is uncertain because defining Viking raid becomes problematic when the raiders have been Christian for generations and their targets include other Christians. The cultural transition from Viking Age to medieval period occurred across several generations, making it impossible to identify a specific moment when the Viking Age ended. At some point, the people we call Vikings stopped existing as a distinct culture and became medieval Scandinavians. Though the transition was gradual enough that contemporaries probably didn't notice they were living through a cultural extinction, what remains are questions we keep asking, knowing the answers are incomplete and provisional. How did they think? What mattered to them? What did they hope to achieve? The evidence suggests pragmatic people making rational decisions with available information, adapting to circumstances, solving problems through accumulated knowledge and occasional innovation. They weren't inherently different from modern people possessed of the same range of intelligence, emotion, and capability. What differed were their circumstances, their knowledge, and their tools. Given different times and technologies, they might have accomplished anything. Given the times and technologies they possessed, they accomplished extraordinary things, crossing oceans, founding settlements, creating literature, and surviving in environments that tested human limits. The Viking legacy isn't a collection of artifacts in museums or genetic markers in populations or words in languages. It's the demonstration that humans, with limited technology and incomplete knowledge, can accomplish extraordinary things through determination, accumulated wisdom, and willingness to risk everything on uncertain ventures. It's the proof that culture can transform rapidly when circumstances demand. It's the reminder that even successful civilizations are temporary, that settlements are abandoned, languages change, and knowledge is lost unless actively preserved. Standing in a museum before a Viking sword, seeing the pattern-welded blade's flowing lines, you're looking at someone's solution to a problem, how to create a weapon that could survive battle. The sword worked well enough that its owner kept it, valued it enough to have it buried with them or pass it to descendants who eventually lost or buried it. The solution survived. The problem, how to forge superior steel, remains solved, though differently. The person who created this solution died a millennium ago, their name forgotten, their thoughts unknown, their legacy reduced to this blade in a display case, labeled with a number and a date range and a two-sentence description that explains everything except what we most want to know. What was it like to be them? That question, what was it like, echoes through everything the Vikings left behind. We can measure, analyze, categorize, and explain their artifacts. We can trace their genetic legacy through populations, map their trade routes through recovered coins, translate their literature from manuscripts. But we cannot recover their experience, the sensation of living in their world with their knowledge and limitations. The gap between physical evidence and lived experience remains unbridgeable, leaving us with increasingly precise information about increasingly distant people whose lives we understand objectively but cannot feel subjectively. The Vikings crossed the North Atlantic 1,000 years ago. The ships that carried them rotted away. The knowledge that guided them was forgotten. The settlements they founded were abandoned or transformed beyond recognition. What remains are fragments enough to know something extraordinary happened, not enough to fully understand how or why. In that gap between evidence and understanding lies the mystery that draws us back to the Viking Age repeatedly, each generation asking new questions of old evidence, seeking connections to people who lived so differently yet remained fundamentally human, solving human problems with limited tools and incomplete knowledge, leaving behind traces we continue deciphering, knowing the complete story will never be recovered, but the attempt to understand enriches our own understanding of what humans can accomplish and what time inevitably erases.